Close your eyes and let yourself drift as we journey through time itself, back through billions of years to witness the magnificent story of our cosmic home. Tonight we'll travel from the very beginning, when our solar system was nothing more than a whisper of possibility in a vast molecular cloud, all the way to its distant future, billions of years from now. 4.5 billion years ago, in a quiet arm of the Milky Way galaxy, something extraordinary was about to happen. Where we now orbit peacefully around our sun, there existed only a vast expanse of cold molecular hydrogen, helium, and tiny grains of cosmic dust. This enormous cloud, stretching perhaps 100 light-years across, drifted silently through space, a stellar nursery waiting for the right moment to give birth. The molecular cloud that would become our solar system wasn't alone in the cosmos. Throughout our galaxy, thousands of similar clouds float between the stars, each one a potential birthplace for new suns and planets. These clouds form from the accumulated debris of previous generations of stars, enriched with heavier elements forged in stellar furnaces and scattered by supernova explosions. Our particular cloud contained not just the primordial hydrogen and helium from the universe's birth, but also carbon, oxygen, nitrogen, silicon, iron, and dozens of other elements created by stars that lived and died long before our sun was born. The temperature within this cloud hovered just above absolute zero, perhaps 10 or 20 degrees Kelvin. At such frigid temperatures, atoms moved slowly, barely colliding with one another. The cloud's density, while greater than the surrounding interstellar medium, was still incredibly sparse by earthly standards. If you could have taken a cubic centimetre of this cloud, you would have found perhaps 1,000 particles within it, compared to the 30 billion molecules in a cubic centimetre of air at sea level on Earth today. For millions of years, this cloud existed in a delicate equilibrium. The mutual gravitational attraction of all its particles tried to pull it together, while the random thermal motion of its atoms and molecules, slight as it was, pushed outward. Additionally, magnetic fields threaded through the cloud, providing another source of support against gravitational collapse. The cloud rotated slowly, perhaps completing one full turn every few million years, and this rotation would prove crucial for what was to come. Within this vast cloud, slight variations in density existed. Some regions contained a few more particles per cubic centimetre than others. These denser regions exerted slightly stronger gravitational pulls on their surroundings, gradually attracting more material. Over millions of years, these density variations grew more pronounced, creating a lumpy, irregular structure throughout the cloud. The cloud wasn't isolated from its galactic environment. Stellar winds from nearby stars pushed against its boundaries. Ultraviolet radiation from hot, young stars in neighbouring regions heated its outer layers. Cosmic rays, high-energy particles accelerated by distant supernovae and other violent events, penetrated deep into the cloud, ionizing atoms and affecting the cloud's chemistry. All these external influences played roles in shaping the cloud's evolution. Deep within the cloud, molecules formed and reformed in a slow cosmic chemistry. Hydrogen molecules dominated, but more complex species also emerged. Water, methanol, ammonia, and even simple organic molecules like formaldehyde assembled atom by atom on the surfaces of tiny dust grains. These grains, typically less than a micrometer across, served as cosmic laboratories where atoms could meet and bond more easily than in the near vacuum of open space. The dust grains themselves were fascinating objects, built up over millions of years from silicon, carbon, and other heavy elements. Some were crystalline, others amorphous. Many were coated with mantles of ice, creating tiny worlds of frozen water, carbon dioxide, and other compounds. These grains would eventually become the building blocks of planets, carrying water and organic molecules to newly formed worlds. As time passed, the cloud continued its slow evolution. Turbulent flows within it created swirling eddies and currents. Shock waves from distant supernova occasionally passed through, compressing some regions while rarefying others. The cloud's connection to the galactic magnetic field meant that any change in its density or motion had to drag magnetic field lines along with it, a process that slowed its evolution but also helped determine its ultimate structure. The region that would become our solar system was located roughly 26,000 light-years from the galactic centre, in what astronomers call the Orion Arm or local arm of the Milky Way. This location would prove fortuitous, far enough from the galactic centre to avoid its intense radiation and frequent supernova, yet not so far into the galactic outskirts that heavy elements were scarce. It provided an ideal environment for the formation of a planetary system capable of supporting life. Around this time, something significant happened nearby. Perhaps a massive star in the region reached the end of its life and exploded as a supernova, or maybe the cloud passed through a region of enhanced stellar density, where the combined stellar winds and radiation from multiple stars provided an external push. Whatever the trigger, a wave of compression began to move through our molecular cloud. This compression wave wasn't dramatic by human standards. The density increase might have been just a factor of 2 or 3, but in the delicate balance between gravity and pressure that had kept the cloud stable for millions of years, this was enough to tip the scales. In the region that would become our solar system, gravity began to win. As the compression wave passed, it left behind a region slightly denser than before. This denser region's enhanced gravity pulled in more material from its surroundings, which increased its density further, which strengthened its gravitational pull even more. A runaway process had begun. What had been a stable, if lumpy, part of the molecular cloud was now beginning its transformation into something new. The collapsing region wasn't spherical. The cloud's initial rotation, slight as it was, meant that material falling inward from different directions carried different amounts of angular momentum. As the collapse proceeded, this rotation became more pronounced. The conservation of angular momentum, the same principle that causes figure skaters to spin faster when they pull their arms close to their bodies, meant that as the cloud contracted, it spun more rapidly. This increasing rotation had a profound effect on the collapse. While material could fall relatively freely along the rotation axis, motion perpendicular to this axis was resisted by centrifugal force. The result was that the collapsing cloud began to flatten, transforming from a roughly spherical region into a disc-like structure. This disc, known as a protoplanetary or propylid disk, would become the birthplace of all the planets, moons, asteroids, and comets in our solar system. The collapse wasn't uniform or smooth. Turbulence within the infalling material created complex patterns of motion. Magnetic fields, dragged along with the collapsing gas, became twisted and amplified. In some regions, the magnetic pressure became strong enough to temporarily halt or even reverse the infall, creating complex structures of inflowing and outflowing material. As more and more material fell inward, the central region of the collapsing cloud grew increasingly dense and hot. The gravitational potential energy of the infalling material was converted into kinetic energy, heating the gas. At first, this heat could escape relatively easily as infrared radiation, keeping the temperature low. But as the density increased, the cloud became more opaque to its own radiation. Heat began to build up in the core. The temperature in the central region rose from 20 Kelvin to 100, then 1,000. The core began to glow, first in the infrared, invisible to human eyes but detectable by the warm radiation it emitted. This glowing core, not yet a true star, but no longer just a cloud of gas, had become what astronomers call a protostar. Meanwhile, the surrounding disk continued to grow and evolve. Material from the original molecular cloud continued to rain down onto the disk, adding mass and angular momentum. The disk extended outward for hundreds of astronomical units, far beyond the current orbit of Neptune. Its inner edge, however, couldn't extend all the way to the forming protostar. The intense heat and radiation from the central object created a cleared region, a gap between the star and the disk's inner edge. Within the disk, a complex interplay of forces shaped its structure. Gravity tried to pull material inward toward the protostar. Rotation created centrifugal force that supported the disk against collapse. Pressure from the heated gas pushed outward. Magnetic fields, now strongly amplified by the collapse and differential rotation of the disk, created additional stresses and torques. The disk wasn't uniform in composition. Temperature varied dramatically with distance from the protostar. Close to the center, where temperatures exceeded 1,000 Kelvin, only refractory materials like iron and rocky minerals could exist in solid form. Water and other volatile compounds were vaporized. Farther out, where temperatures dropped below the freezing point of water, ice could form. This transition point, called the frost line or snow line, would prove crucial in determining the architecture of the planetary system to come. The process of collapse and disk formation took roughly 100,000 years, a mere instant in cosmic terms, but an eternity by human standards. During this time, the disk's mass grew to perhaps 1% of the central protostar's mass, containing enough material to form all the planets we know today, and much more besides. As the disk evolved, instabilities began to develop within it. Gravitational interactions between different parts of the disk created spiral waves, similar to those seen in spiral galaxies, but on a much smaller scale. These waves concentrated material in some regions while clearing it from others. Turbulence, driven by temperature differences and magnetic effects, created a complex, ever-changing pattern of flows and eddies. The protostar at the disk's center continued to grow, feeding on material from the inner edge of the disk. This accretion process wasn't steady or quiet. Material didn't simply flow smoothly onto the star. Instead, it accumulated at the disk's inner edge until instabilities developed, then fell onto the protostar in sudden bursts. These accretion events released enormous amounts of energy, causing the protostar to flare dramatically in brightness. Some of the infalling material didn't make it onto the protostar. The interaction between the disk's magnetic field and that of the protostar created powerful magnetic torques that could fling material outward. Additionally, the intense radiation pressure from accretion events could drive powerful winds from the disk's surface. Some of this material was launched in narrow jets along the protostar's rotation axis, creating bipolar outflows that extended for light years into the surrounding molecular cloud. These jets and outflows played a crucial role in the system's evolution. They carried away angular momentum, allowing the protostar to continue accreting material without spinning up to the point where it would tear itself apart. They also began to clear away the remaining envelope of gas from the original molecular cloud, gradually revealing the forming star system to the universe beyond. Deep within the swirling disk of gas and dust, the protostar that would become our Sun continued its remarkable transformation. The temperature at its core had risen to several 100,000 Kelvin, hot enough that hydrogen atoms were completely ionized, existing as separate protons and electrons rather than neutral atoms. The density had increased to the point where this ionized gas or plasma behaved almost like a liquid, flowing and convecting in complex patterns. The protostar's energy came entirely from gravitational contraction at this stage. As material continued to fall inward and the core compressed under its own weight, gravitational potential energy converted into heat. This process, known as Kelvin-Helmholtz contraction, would continue for millions of years, gradually raising the core temperature toward the critical threshold needed for nuclear fusion. The young protostar was far from stable during this period. Convection cells, vast columns of rising hot gas and descending cooler material, transported energy from the deep interior to the surface. These convection cells were enormous, each one comparable in size to the protostar's radius. As hot gas rose to the surface, it cooled and released its energy as radiation, then sank back down to be reheated in the depths. The surface of the protostar during this time would have appeared alien to anyone familiar with our current sun. Instead of the relatively calm photosphere we see today, marked only by sunspots and occasional flares, the young proto-sun's surface seethed with activity. Giant convection cells created a constantly changing pattern of bright and dark regions. Powerful magnetic fields, generated by the motion of charged particles within the convecting interior, emerge from the surface in complex, tangled configurations. These magnetic fields drove spectacular activity. Where magnetic field lines emerged from and re-entered the surface, they created active regions far more powerful than anything we see on the sun today. Flares, explosive releases of magnetic energy, occurred frequently and with tremendous intensity. Some of these flares released as much energy in minutes as the present-day sun emits in weeks. The protostar's rotation played a crucial role in its magnetic activity. Still spinning rapidly from the angular momentum inherited from the collapsing cloud, the young sun completed a rotation in just a few days. Compared to the 25 to 35 days it takes different parts of the sun to rotate today. This rapid rotation, combined with the convective motion, created a powerful magnetic dynamo that generated fields thousands of times stronger than the sun's current magnetic field. As the protostar continued to contract, its core temperature rose inexorably. At 1 million Kelvin, 2 million, 5 million, the conditions grew ever more extreme. The density at the center reached tens of grams per cubic centimeter, several times denser than lead. The pressure exceeded billions of atmospheres. Under these conditions, protons began to move fast enough that when they collided, they could occasionally overcome their mutual electrical repulsion and get close enough for the strong nuclear force to take effect. At first, these nuclear reactions were sporadic and contributed negligibly to the protostar's energy output. The primary reaction that occurred was the fusion of deuterium, a heavy isotope of hydrogen, with regular hydrogen to form helium-3. Deuterium fusion can occur at lower temperatures than regular hydrogen fusion, beginning at around 1 million Kelvin. However, deuterium was rare, making up only about 20 parts per million of the hydrogen in the protostar, so this energy source was quickly exhausted. The protostar continued to contract, and the core temperature continued to rise. At around 10 million Kelvin, a crucial threshold was crossed. At this temperature, regular hydrogen nuclei, simple protons, moved fast enough that a significant number of collisions resulted in fusion reactions. The proton-proton chain, the series of nuclear reactions that would power our sun for billions of years, had begun. The ignition of hydrogen fusion marked the birth of our sun as a true star. The energy released by fusion created an outward pressure that finally balanced the inward pull of gravity. The contraction that had been proceeding for millions of years slowed and then stopped. The sun had reached hydrostatic equilibrium, the stable balance between gravity and pressure that defines a main sequence star. This transition wasn't instantaneous or smooth. As fusion reactions began to contribute significantly to the sun's energy output, the internal structure had to readjust. The convection patterns changed. The core, now generating its own energy rather than just compressing, developed a different temperature and density profile. These adjustments took hundreds of thousands of years to complete, during which the sun's brightness and temperature fluctuated. The young sun that emerged from this process was similar to, yet different from, the star we know today. It was roughly the same size, about 1.4 million kilometers in diameter. Its surface temperature was comparable, around 5700 Kelvin, but it was significantly less luminous, shining with only about 70% of its current brightness. This lower luminosity would have profound implications for the planets forming around it. The sun's composition at this time reflected that of the molecular cloud from which it formed. By mass, it was about 71% hydrogen, 27% helium, and 2% heavier elements. These heavier elements, though a small fraction of the total, were crucial. They provided opacity, helping trap radiation within the sun and affecting its internal structure. They also served as catalysts for certain fusion reactions and would eventually enable the formation of rocky planets. Even as a newly minted star, the sun continued to interact dramatically with its surrounding disk. Its radiation, now powered by steady fusion rather than sporadic accretion, began to heat the inner regions of the disk more consistently. The innermost material, within about 0.1 astronomical units, was hot enough that even refractory materials like iron and aluminum oxide could exist only as vapor. The sun's stellar wind, a stream of charged particles flowing outward from its surface, began to clear away gas from the inner disk. This wind was much stronger in the young sun than it is today, perhaps 1,000 times more powerful. Combined with the pressure of the sun's radiation, it began to push lighter elements, particularly hydrogen and helium, outward from the inner solar system. The sun's powerful magnetic field also played a crucial role in shaping the disk. Where the sun's magnetosphere met the disk, complex interactions occurred. In some theories, magnetic field lines connecting the sun to the disk helped transfer angular momentum outward, allowing the sun to slow its rotation while enabling continued accretion. These magnetic connections also channeled material from the disk onto the sun along preferred paths, creating hotspots where infalling material struck the stellar surface. The young sun's activity had profound effects on the disk's chemistry. Intense ultraviolet radiation broke apart molecules, creating a rich chemistry in the disk's upper layers. X-rays from flares penetrated deeper, ionizing atoms and driving chemical reactions that wouldn't otherwise occur at the disk's relatively low temperatures. High-energy particles accelerated by the sun's magnetic field irradiated dust grains, creating isotopic anomalies that we can still detect in meteorites today. One of the most significant effects of the early sun was the creation and processing of calcium-aluminum-rich inclusions, or CAIs. These millimetre to centimetre-sized objects, found today in certain meteorites, were among the first solids to condense in the solar system. They formed in the hot inner regions of the disk, where temperatures exceeded 1300 Kelvin, allowing calcium and aluminum oxides to condense, while more volatile materials remained gaseous. The formation of CAIs marked a crucial milestone in solar system history. Radiometric dating of these objects gives us the precise birth date of our solar system, 4.567 billion years ago. This date represents the moment when the first solids condensed from the solar nebula, beginning the process of planet formation. Shortly after CAIs formed, they were somehow transported outward through the disk. Some scientists believe they were lofted above the disk by magnetic fields or stellar winds, then fell back down at greater distances from the sun. Others suggest they were carried outward by turbulent mixing or spiral waves in the disk. However it happened, this outward transport meant that these earliest solids became incorporated into bodies forming throughout the solar system. Following the CAIs, other types of solid particles began to condense from the cooling nebula. At temperatures around 1200 Kelvin, iron and nickel condensed as tiny metallic grains. As temperatures dropped further, silicate minerals like olivine and pyroxene formed. These minerals would become the primary building blocks of the terrestrial planets. The condensation sequence depended critically on distance from the Sun. Close to the Sun, only the most refractory materials could condense. Moving outward, progressively more volatile materials could solidify. At about 2.7 astronomical units from the Sun, temperatures dropped below 370 Kelvin, allowing water ice to condense. This location, the frost line, marked a fundamental division in the solar system's architecture. Inside the frost line, solid particles consisted primarily of rock and metal, materials that made up only about 0.6% of the disk's mass. Outside the frost line, water ice could condense, and since oxygen was the third most abundant element in the nebula after hydrogen and helium, this dramatically increased the amount of solid material available. Beyond the frost line, the surface density of solids was perhaps 4 times higher than in the inner solar system. As solid particles condensed and grew, they began to settle toward the disk's midplane. Larger particles settled faster than smaller ones, creating a thin, dense layer of dust and small rocks in the middle of the disk. This concentration of solid material in the midplane would prove crucial for the next stage of planet formation. The young Sun continued to evolve during this period. Its rotation gradually slowed as angular momentum was carried away by stellar winds and transferred to the disk through magnetic interactions. The power of its stellar wind decreased, though it remained much stronger than today. The frequency and intensity of flares diminished, though the young Sun remained far more active than the sedate star we know today. In the warm inner regions of the protoplanetary disk, within about 4 astronomical units of the young Sun, a remarkable process was beginning. The tiny grains of metal and rock that had condensed from the cooling nebula were starting their long journey toward becoming planets. This process would unfold over millions of years, transforming microscopic dust particles into worlds thousands of kilometers across. The first stage of this transformation occurred through gentle collisions. As dust grains orbited the Sun, slight differences in their orbital velocities caused them to occasionally bump into one another. When 2 grains collided at low speeds, less than a meter per second, electrostatic forces and van der Waals interactions could cause them to stick together. These forces, though weak, were sufficient to bind tiny particles into loose, fluffy aggregates. These early aggregates were incredibly fragile structures, more like cosmic dust bunnies than solid rocks. They were highly porous, with densities perhaps only 1% that of solid rock. A slight jostle could break them apart, yet in the calm environment of the disk's midplane, many survived and continued to grow. As they accumulated more dust grains, they evolved from fluffy aggregates into more compact structures, though still far more porous than the rocks we see on Earth today. The growth process accelerated as particles reached millimeter and centimeter sizes. Larger particles had greater cross-sections for collision and stronger gravitational fields, allowing them to sweep up smaller grains more efficiently. However, this stage of growth faced a significant challenge known as the meter barrier. As particles grew from centimeter to meter sizes, they became large enough to experience significant gas drag, but not massive enough for their gravity to dominate their motion. Gas drag caused these meter-sized particles to spiral inward toward the Sun, potentially falling into the star before they could grow larger. Additionally, Collisions between similar-sized objects at this scale often resulted in fragmentation rather than growth, as impact velocities exceeded the weak binding forces holding the aggregates together. How planetesimals overcame this barrier remains one of the most debated topics in planetary science. One solution may have been the rapid concentration of particles in specific regions of the disk. Turbulence in the disk created temporary pressure maxima, where particles could accumulate. If enough material concentrated in these regions, gravitational instabilities could cause rapid collapse, bypassing the problematic meter size range entirely. This process, called streaming instability, could form kilometre-sized planetesimals directly from centimetre-sized pebbles. However planetesimals formed, by 10,000 years after the Sun's birth, the inner solar system contained millions of these kilometre-sized bodies. These planetesimals were the true building blocks of planets, massive enough that their own gravity dominated their evolution. When two planetesimals collided, they were more likely to merge than to fragment, beginning a new phase of growth through gravitational accumulation. The distribution of planetesimals wasn't uniform throughout the inner solar system. Variations in temperature, pressure, and turbulence in the original disk created regions where planetesimals formed more efficiently. These variations would ultimately influence where planets formed and their final compositions. The chemical composition of planetesimals also varied with distance from the Sun, reflecting the temperature-dependent condensation sequence of different materials. As planetesimals grew through collisions and mergers, the largest bodies in each region began to dominate. Their stronger gravity allowed them to attract and capture smaller planetesimals more effectively, leading to runaway growth. A body that was initially just slightly larger than its neighbours would grow faster, becoming ever more dominant. This process could produce moon-sized planetary embryos in as little as 100,000 years. In the region closest to the Sun, where Mercury would eventually form, the environment was particularly harsh. Temperatures exceeded 800 Kelvin even after the disk had cooled somewhat from its initial state. Only the most refractory materials could exist as solids here. Iron, nickel, and minerals rich in calcium, aluminum, and titanium. The lack of lighter materials meant less solid material was available for planet formation. The intense stellar wind and radiation from the young Sun also affected this region more severely than areas farther out. Light gases were quickly stripped away, and even some moderately volatile elements were depleted. The planetesimals forming here were dense and metal-rich, setting the stage for Mercury's unusual composition, with its oversized iron core making up about 75% of the planet's radius. Mercury's formation likely involved numerous violent collisions. One theory suggests that Mercury originally formed as a larger body, perhaps twice its current size, with a composition similar to the other terrestrial planets. A catastrophic impact with another large planetesimal then stripped away much of its rocky mantle, leaving behind the iron-rich world we see today. This impact would have needed to occur at just the right angle and velocity to remove the mantle while leaving the core largely intact. Alternatively, Mercury's high metal content might reflect the composition of planetesimals in the innermost solar system. If most silicate minerals couldn't condense so close to the Sun, or if they were preferentially removed by gas drag or radiation pressure, the remaining planetesimals would naturally be metal-rich. Mercury would then represent the natural outcome of accretion from such materials. The final stages of Mercury's assembly involved a period called late accretion, during which the planet swept up remaining planetesimals in its orbital region. This process was violent, with impacts creating enormous basins and potentially remelting parts of the surface. The Caloris Basin, 1,400 kilometers across, represents one of the last major impacts in Mercury's formation, occurring perhaps 3.9 billion years ago. Moving outward to where Venus formed, conditions were somewhat cooler but still extreme. Temperatures allowed a wider range of minerals to condense, including magnesium-rich silicates like enstatite and forsterite. The greater availability of solid material, combined with Venus's location in a broader, more material-rich part of the disk, allowed it to grow much larger than Mercury. Venus's formation proceeded through the same stages as Mercury's: dust to pebbles, to planetesimals, to embryos. However, Venus grew large enough to begin attracting a significant atmosphere from the surrounding nebula gas. As the planet reached about half its current mass, its gravity became strong enough to capture hydrogen and helium from the disk, along with water vapor and other volatile compounds. This early atmosphere was nothing like Venus's current dense carbon dioxide shroud. It was likely dominated by hydrogen and helium, with water vapor, methane, and ammonia as minor constituents. However, this primordial atmosphere wouldn't last. The intense solar wind from the young sun, combined with Venus's lack of a protective magnetic field, would gradually strip away the lighter elements. The loss of Venus's water is one of the most significant events in its history. Initially, Venus likely had as much water as Earth, either captured from the nebula or delivered by impacting comets and asteroids. However, Venus's proximity to the Sun meant surface temperatures were high enough for water to exist primarily as vapor rather than liquid oceans. In the upper atmosphere, ultraviolet radiation from the Sun broke water molecules apart into hydrogen and oxygen. The light hydrogen atoms could escape to space, while the heavier oxygen atoms remained behind, eventually combining with surface rocks or carbon to form carbon dioxide. Over hundreds of millions of years, this process desiccated Venus, transforming it from a potentially habitable world into the hellish greenhouse we see today. Venus also developed a peculiar rotation unlike any other planet. While most planets rotate in the same direction they orbit, Venus rotates backward, and extremely slowly, taking 243 Earth days to complete one rotation. This unusual spin might have resulted from a massive impact during the late stages of formation, or from tidal interactions with the Sun and Earth over billions of years. Earth's formation story begins in the same protoplanetary disk, at about 1 astronomical unit from the Sun. This distance placed Earth in a particularly favourable location, close enough to the Sun that rocky materials dominated over ices, but far enough that a wide variety of minerals could condense. The temperature here, around 300 to 400 Kelvin during the disk phase, allowed minerals containing moderate amounts of water to form. The early stages of Earth's growth followed the familiar pattern. Dust aggregated into pebbles, pebbles into planetesimals, planetesimals into embryos. By 1 million years after the Sun's formation, dozens of Moon-to-Mars-sized embryos likely orbited in the region where Earth would form. These embryos had roughly circular, coplanar orbits separated by mutual gravitational interactions. For several million years, these embryos continued to grow by sweeping up remaining planetesimals while maintaining relatively stable orbits. However, as the planetesimal population depleted, gravitational perturbations between embryos became more significant. Orbits began to cross, leading to giant impacts between embryo-sized bodies. These giant impacts were catastrophic events that shaped Earth's final structure. When two embryos collided at typical impact velocities of 10 kilometers per second or more, the energy released was sufficient to melt or vaporize large fractions of both bodies. Heavy iron from their cores would sink through the molten rock to merge with Earth's growing core, while lighter silicates formed a magma ocean at the surface. Each major impact reset Earth's geological clock, erasing earlier surface features under seas of molten rock. The energy from these impacts also contributed to Earth's internal heat, driving the differentiation process that separated the planet into a metallic core and rocky mantle. Some impacts may have been energetic enough to vaporize rock, creating a temporary atmosphere of silicon and magnesium vapor that later condensed and rained back down. The most significant impact in Earth's history occurred relatively late in its formation, perhaps 30 to 50 million years after the Sun's birth. A Mars-sized embryo, often called Theia, struck the proto-Earth in a glancing blow. This impact was unique in its outcome. Instead of simply merging with Earth or being destroyed, the collision ejected a disk of debris into orbit around Earth. This orbiting debris, consisting primarily of material from the mantles of both Earth and Theia, quickly coalesced to form the Moon. The process was remarkably fast by geological standards, with most of the Moon assembling within a few thousand years. The newly formed Moon orbited much closer to Earth than it does today, perhaps only 20,000 kilometers away, appearing enormous in Earth's sky and raising tremendous tides in the magma ocean below. The moon-forming impact had profound effects on Earth beyond creating our natural satellite. The impact energy completely melted Earth's upper layers, allowing dense iron from Theia's core to sink and merge with Earth's core. This may explain why Earth's core is proportionally larger than those of Venus or Mars. The impact also likely stripped away any primordial atmosphere Earth had accumulated, requiring a new atmosphere to form from volcanic outgassing and comet impacts. The impact angle and the velocity gave the Earth-Moon system substantial angular momentum, causing Earth to rotate much faster than before. The early Earth completed a rotation in just 5 or 6 hours, making days and nights flash by in quick succession. Over billions of years, tidal friction between Earth and the Moon has slowed this rotation to our current 24-hour day and pushed the Moon outward to its current distance. Mars formed in the outer region of the inner solar system, about 1.5 astronomical units from the Sun. This location, closer to the asteroid belt and the frost line, presented both opportunities and challenges for planet formation. While more material was potentially available, including some water-bearing minerals, the region was also more dynamically unstable. Mars grew rapidly at first, reaching about half its current mass within just 2 to 4 million years. This rapid early growth is recorded in Martian meteorites, which show that Mars's core formed very early, within the first few million years of solar system history. However, unlike Earth, Mars's growth then stalled. It never grew massive enough to dominate its orbital region completely. Several factors likely contributed to Mars's stunted growth. The nearby presence of Jupiter, which was forming contemporaneously, gravitationally stirred up planetesimals in Mars's region, increasing their velocities and making them harder to capture. Many planetesimals that might have been accreted by Mars were instead scattered inward toward Earth and Venus, or outward toward the asteroid belt. Mars's small size had significant consequences for its evolution. With less gravitational compression and radioactive heating than Earth, Mars cooled more quickly. Its magnetic field, generated by convection in its liquid iron core, shut down relatively early, perhaps 4.1 billion years ago. Without a protective magnetic field, Mars became vulnerable to solar wind erosion of its atmosphere. Early Mars was likely much more Earth-like than the cold, dry world we see today. Evidence from rovers and orbiters shows that liquid water once flowed on Mars's surface, carving river valleys and filling lake basins. Mars probably had a thicker atmosphere, perhaps dense enough to support a water cycle with rain and snow. Some scientists even speculate that early Mars might have had a northern ocean covering much of its lowland hemisphere. The transformation of Mars from a potentially habitable world to a frozen desert occurred over hundreds of millions of years. As Mars's interior cooled and its magnetic field failed, solar wind began stripping away its atmosphere. Lower atmospheric pressure meant water could no longer exist as a liquid on the surface. The remaining water froze into permafrost and polar ice caps, or was lost to space. Carbon dioxide, the main component of Mars's atmosphere, partially froze out at the poles or was absorbed into rocks. Despite these changes, Mars retained enough atmosphere to support global dust storms and seasonal changes. Its two small moons, Phobos and Deimos, likely captured asteroids or remnants from a long-ago impact, orbit close to the planet. Phobos, the larger and closer moon, orbits so close that tidal forces are gradually pulling it apart. In about 50 million years, it will either crash into Mars or break up into a ring system. Between Mars and Jupiter lies a region that tells a story of planetary formation interrupted. The asteroid belt, stretching from about 2 to 3.5 astronomical units from the Sun, contains millions of rocky and metallic bodies ranging from dust grains to the dwarf planet Ceres, nearly 1,000 kilometers across. This region marks a fundamental transition in our solar system, the boundary between the terrestrial planets and the gas giants. The total mass of all asteroids combined equals only about 4% of the Moon's mass, far less than a planet. Yet this wasn't always the case. During the solar system's formation, this region likely contained enough material to form a planet several times Earth's mass. The story of why this planet never formed and where all that material went reveals the profound influence of Jupiter on the solar system's architecture. In the early solar system, the region now occupied by the asteroid belt was rich with planetesimals. The temperature here, around 150 to 200 Kelvin during the disk phase, was cold enough for some water ice to condense, especially in the outer regions. This meant planetesimals forming here contained both rocky materials and varying amounts of water ice, creating a diverse population of objects with different compositions. Initially, these planetesimals began the same growth process seen in the inner solar system. They collided and merged, gradually building larger bodies. Several dozen embryos, some possibly Mars-sized or larger, likely formed in this region within the first few million years. Had they been left undisturbed, these embryos might have eventually merged into a single planet. However, Jupiter's rapid formation in the neighbouring region changed everything. As Jupiter grew to its enormous size, its gravity began to stir up the orbits of nearby planetesimals. Objects that had been on relatively circular orbits were pulled into elongated ellipses. Their velocities relative to one another increased dramatically, transforming gentle mergers into catastrophic collisions. When planetesimals collided at these higher velocities, they shattered rather than merged. Instead of building larger bodies, collisions began breaking them apart into smaller fragments. This collisional, grinding process, continuing for billions of years, has reduced most of the belt's mass to small fragments. The asteroids we see today are either surviving planetesimals that avoided catastrophic collisions or fragments of larger bodies that were destroyed. Jupiter's influence extended beyond simply stirring up orbits. The giant planet's gravity created regions of orbital resonance throughout the asteroid belt. These resonances occur where an asteroid's orbital period forms a simple ratio with Jupiter's period. For example, at the 3:1 resonance, an asteroid orbits the Sun 3 times for every one Jupiter orbit. At these locations, repeated gravitational tugs from Jupiter can dramatically alter an asteroid's orbit, often ejecting it from the belt entirely. These resonances carved gaps in the asteroid belt, known as Kirkwood gaps, after their discoverer. The most prominent gaps occur at the 3:1, 5:2, 7:3, and 2:1 resonances with Jupiter. Over billions of years, asteroids that wandered into these resonances were ejected, creating relatively empty zones that divide the belt into distinct regions. Not all resonances are destructive. Some, like the 3-2 resonance with Jupiter, can actually stabilize orbits. The Hilda asteroids occupy this resonance, forming a dynamic group that remains stable despite their proximity to Jupiter. Similarly, the Trojan asteroids share Jupiter's orbit, clustered around stable points 60 degrees ahead of and behind the giant planet. The asteroid belt's composition varies systematically with distance from the Sun, preserving a record of conditions in the early solar system. In the inner belt, closer to Mars, most asteroids are S-types, composed primarily of silicate minerals with some metal. These bodies formed at temperatures too high for water ice to condense, resulting in dry, rocky compositions similar to the inner planets. Moving outward through the belt, C-type asteroids become dominant. These carbonaceous asteroids contain organic compounds and hydrated minerals, indicating they formed where water ice could condense and later react with rocky materials. Some C-types contain up to 20% water by mass, locked in the crystal structure of clay minerals. In the outer reaches of the belt, P-type and D-type asteroids appear. These extremely dark objects, reflecting less than 5% of sunlight, are rich in organic compounds and possibly water ice. Their compositions suggest they formed even farther from the Sun and were later scattered inward to their current locations. Ceres, the belt's only dwarf planet, deserves special attention. At 940 kilometers in diameter, Ceres contains about 25% of the belt's total mass. Unlike smaller asteroids, Ceres is massive enough that gravity has pulled it into a spherical shape. More remarkably, Ceres is differentiated, with a rocky core surrounded by an icy mantle that may contain more water than all Earth's oceans. Recent observations by NASA's Dawn spacecraft revealed that Ceres is far from a dead world. Bright spots in some craters appear to be deposits of salts, possibly from briny water erupting from below. Some regions show evidence of recent geological activity, including possible cryovolcanism, where water and other volatiles play the role that molten rock plays on Earth. Ceres may even harbour a subsurface ocean of liquid water, kept from freezing by dissolved salts and possibly ammonia. Vesta, the second most massive asteroid, tells a different story. This 530-kilometre body is dry and differentiated, with a basaltic crust overlying an olivine mantle and iron core. Vesta is likely an intact protoplanet, one of the original embryos that formed in the asteroid belt. Its heavily cratered surface records billions of years of impacts, including one enormous collision that excavated a crater nearly as wide as Vesta itself. That giant impact on Vesta ejected millions of fragments into space, creating a family of asteroids with similar orbits and compositions. These Vestoids, along with pieces knocked off by later impacts, have found their way to Earth as meteorites. The heady meteorites, Howardites, Eucrites, and Diogenites all come from Vesta, giving us actual samples of a protoplanet's crust and mantle. Many other asteroids show evidence of families created by catastrophic collisions. The Eos family, containing over 9,000 members, formed when a 190-kilometre parent body shattered about 1 billion years ago. The Themis family resulted from the breakup of a 400-kilometre parent body. These families gradually disperse over time as subtle gravitational and thermal forces alter their orbits, but many remain recognizable even after hundreds of millions of years. Some asteroids are rubble piles, collections of fragments held together by weak gravity rather than material strength. The asteroid Itokawa, visited by Japan's Hayabusa spacecraft, exemplifies this structure. Only 500 meters long, Itokawa consists of boulders and gravel with 40% empty space between the fragments. Such bodies can survive impacts that would shatter solid rocks, as the loose structure absorbs impact energy. Other asteroids appear to be contact binaries, two separate bodies resting against each other. The asteroid Arakoth, visited by New Horizons in the Kuiper Belt, but similar to some main belt asteroids, shows this structure clearly. These objects likely formed when two bodies gently came together at very low velocity, perhaps just walking speed, and stuck. The asteroid belt continues to evolve today. Collisions still occur, occasionally creating temporary clouds of dust visible from Earth as zodiacal light. The Yarkovsky effect, a subtle force caused by the uneven heating and cooling of rotating asteroids, gradually changes their orbits. Smaller asteroids can have their rotation rates altered by sunlight, sometimes spinning them up until they fly apart. Some asteroids don't stay in the belt. Jupiter's resonances and close encounters with Mars can eject asteroids onto planet-crossing orbits. These become near-Earth asteroids, potential impactors, but also accessible targets for spacecraft missions. Others are ejected from the solar system entirely or fall into the Sun. Over the solar system's history, the asteroid belt has lost perhaps 99% of its original mass through these processes. The asteroid belt also exchanges material with other regions of the solar system. Some main belt asteroids may be captured comets, former Kuiper belt objects, whose ice has sublimated away, leaving dark, organic-rich surfaces. Conversely, some objects in the outer solar system may be asteroids scattered outward during the giant planet's migration. Beyond the asteroid belt, at 5.2 astronomical units from the Sun, the character of our solar system changes dramatically. Here orbits Jupiter, a world so massive that it contains more than twice the material of all other planets combined. Its formation story differs fundamentally from the terrestrial planets, involving processes that could only occur in the cold outer reaches of the early solar system. Jupiter began forming very early, perhaps within the first million years after the Sun's birth. At its orbital distance, temperatures in the protoplanetary disk were cold enough, about 120 Kelvin, for water ice to condense. This dramatically increased the amount of solid material available for planet building. While the inner solar system had only rocky materials comprising about 0.5% of the disk's mass, the Jupiter-forming region had rocks plus ice, totaling about 2% of the available material. The abundance of solid material allowed planetesimals to grow rapidly in Jupiter's zone. Within perhaps 100,000 years, numerous large planetesimals had formed. These quickly merged into planetary embryos, and one embryo in particular began to dominate. This proto-Jupiter grew faster than its neighbours, its increasing gravity allowing it to capture smaller bodies more effectively. The crucial difference between Jupiter's formation and that of the terrestrial planets occurred when this embryo reached about 10 Earth masses. At this size, its gravity became strong enough to begin capturing hydrogen and helium gas directly from the surrounding nebula. This marked the beginning of runaway gas accretion, a process that would transform a large rocky icy body into a gas giant. Initially, gas accretion proceeded slowly. The embryo's gravity pulled in surrounding gas, but as this gas fell inward, it heated up through compression. This hot gas created pressure that resisted further accretion. The rate of gas capture was limited by how quickly this heat could radiate away into space. For perhaps 1 million years, Jupiter grew gradually, reaching about 20 Earth masses. Then something remarkable happened. Once Jupiter's mass exceeded a critical threshold, roughly 20 to 30 Earth masses, the situation changed dramatically. The planet's gravity became strong enough to overcome the thermal pressure of the infalling gas. Runaway accretion began, with Jupiter capturing gas at an ever-increasing rate. Within just a few 100,000 years, Jupiter grew from 30 Earth masses to its current size of 318 Earth masses. This rapid growth couldn't continue indefinitely. As Jupiter consumed gas from its orbital zone, it created a gap in the disk. Fresh gas flowing in from other regions couldn't keep pace with Jupiter's appetite. Additionally, the young sun's stellar wind was beginning to clear gas from the entire disk. Jupiter's growth ceased not because it reached some maximum size, but because it ran out of available gas to capture. The composition Jupiter acquired during this formation process reflects both its solid embryo and gaseous envelope. The planet consists primarily of hydrogen and helium in roughly the same proportions as the Sun, about 71% hydrogen and 24% helium by mass. However, Jupiter is enriched in heavier elements compared to the Sun, containing perhaps 20 to 40 Earth masses of elements heavier than helium. These heavy elements exist throughout Jupiter, but are concentrated toward the center. Deep within Jupiter likely lies a core of rock and ice, perhaps 10 to 20 Earth masses, surrounded by a layer of metallic hydrogen, a bizarre form of hydrogen that exists only under extreme pressure. Above this lies molecular hydrogen, gradually transitioning to the gaseous atmosphere we observe. Jupiter's rapid formation had profound effects on the rest of the solar system. Its gravity stirred up the asteroid belt, preventing planet formation there. It also affected the formation of Saturn and the other outer planets. Some models suggest Jupiter's early growth might have temporarily halted Saturn's formation by monopolizing available gas in the outer disk. Even more dramatically, Jupiter may have migrated inward after forming. In the Grand Tack model, interactions between Jupiter and the gaseous disk caused it to spiral inward, perhaps reaching as close as 1.5 astronomical units from the Sun, where Mars orbits today. This inward migration would have scattered asteroids and planetesimals throughout the solar system, potentially depleting Mars's feeding zone and delivering water-rich bodies to the inner planets. If this migration occurred, Jupiter didn't remain in the inner solar system. As Saturn formed and grew massive enough, the two giants became locked in a resonant configuration. Their combined gravitational influence on the disk reversed Jupiter's migration, causing both planets to move outward to approximately their current positions. This complex dance, if it occurred, reshaped the entire solar system's architecture. As Jupiter settled into its final orbit, it began capturing a retinue of moons. The four largest, Io, Europa, Ganymede, and Callisto, discovered by Galileo in 1610, are worlds in their own right. These Galilean satellites likely formed from a disk of material orbiting Jupiter, similar to how planets formed around the Sun. Their compositions vary systematically, with distance from Jupiter, with rocky Io closest and ice-rich Callisto farthest, echoing the solar system's overall structure. Io, the innermost Galilean moon, is the most volcanically active body in the solar system. Tidal heating, caused by Jupiter's enormous gravity and resonant interactions with Europa and Ganymede, continuously kneads Io's interior, generating heat that powers hundreds of volcanoes. These volcanoes have resurfaced Io so completely that no impact craters are visible, and sulfur compounds from the eruptions give Io its distinctive yellow-orange colour. Europa, the second Galilean satellite, harbours one of the solar system's most intriguing secrets, a global ocean of liquid water beneath its icy crust. Tidal heating, though less extreme than on Io, keeps this ocean from freezing. The ocean may contain twice as much water as all Earth's oceans combined, and might possess conditions suitable for life. Dark lines crisscrossing Europa's surface appear to be fractures where ocean water has welled up and frozen, suggesting active exchange between the ocean and surface. Ganymede, the largest moon in the solar system, exceeds Mercury in size. It's the only moon known to generate its own magnetic field, indicating a liquid iron core or a subsurface ocean of salty water. Ganymede's surface displays two distinct terrain types: dark, heavily cratered regions billions of years old, and brighter regions with grooved terrain formed by tectonic activity. Callisto, the outermost Galilean moon, is perhaps the most heavily cratered object in the solar system. Its ancient surface, unchanged for billions of years, preserves a record of the early solar system's bombardment history. Despite its battered appearance, Callisto may harbour a subsurface ocean, though buried deeper than Europa's and less likely to interact with the surface. Beyond the Galilean moons, Jupiter possesses dozens of smaller satellites. The inner moons, orbiting closer than Io, are small, irregular bodies likely captured from the asteroid belt or debris from impacts. 4 of these, Metis, Adrastea, Amalthea, and Thebe, orbit within Jupiter's ring system and help maintain it by supplying dust particles. Jupiter's rings, discovered by Voyager 1 in 1979, are far fainter than Saturn's spectacular rings. They consist primarily of microscopic dust particles kicked off the inner moons by micrometeorite impacts. The main ring, about 6,000 kilometers wide, but only 30 kilometers thick, contains enough material to make a body just a few kilometers across, if consolidated. The outer moons of Jupiter form a complex system of captured bodies. These irregular satellites, numbering over 70, orbit far from Jupiter in elongated, often retrograde orbits. They fall into several families, suggesting they are fragments of larger bodies broken apart by collisions. The largest, Himalaya, is only 170 kilometers across, tiny compared to the Galilean giants. Jupiter's magnetic field, the strongest of any planet, extends far into space, creating a magnetosphere that would appear larger than the full moon if visible from Earth. This magnetic field, generated by convection in Jupiter's metallic hydrogen layer, traps charged particles in radiation belts far more intense than Earth's Van Allen belts. These radiation belts pose significant challenges for spacecraft visiting Jupiter and would be lethal to unprotected humans. The Great Red Spot, Jupiter's most famous feature, is a storm larger than Earth that has raged for at least 350 years, and possibly much longer. This anticyclonic storm, rotating counterclockwise in Jupiter's southern hemisphere, is maintained by Jupiter's rapid rotation and the lack of land surfaces to disrupt it. The storm's red colour likely comes from compounds brought up from deeper in the atmosphere and chemically altered by ultraviolet radiation. Jupiter's atmosphere displays a complex pattern of bands and zones, light-coloured zones of rising gas alternating with darker belts of descending gas. These bands are driven by Jupiter's rapid rotation, completing a turn in just under 10 hours, despite the planet's enormous size. The boundaries between bands are marked by powerful jet streams, with winds reaching speeds of 600 kilometers per hour. Deep within Jupiter's atmosphere, conditions become increasingly extreme. Pressure rises to millions of times Earth's surface pressure, and temperatures reach thousands of degrees. Under these conditions, hydrogen behaves in ways never seen on Earth. At about 13,000 kilometers below the cloud tops, hydrogen transforms into a metallic state, conducting electricity like a metal while remaining fluid. Jupiter continues to contract slowly under its own gravity, releasing heat left over from its formation. This internal heat source means Jupiter radiates about twice as much energy as it receives from the Sun. In essence, Jupiter is still cooling off from its rapid formation 4.5 billion years ago, slowly shrinking by about 2 centimeters per year. At 9.5 astronomical units from the Sun, nearly twice Jupiter's distance, Saturn reigns as the solar system's second giant. Though slightly smaller than Jupiter, Saturn is in many ways more complex and mysterious. Its spectacular ring system, diverse collection of moons, and dynamic atmosphere make it one of the most fascinating worlds in our cosmic neighbourhood. Saturn's formation began shortly after Jupiter's, but proceeded somewhat differently. As Jupiter grew massive and began clearing gas from its orbital zone, it affected the availability of material for Saturn's growth. Some models suggest Saturn's core took longer to reach the critical mass needed for runaway gas accretion, perhaps 3 to 4 million years compared to Jupiter's 1 to 2 million years. This delayed formation had significant consequences. By the time Saturn began rapid gas accretion, the protoplanetary disk had less gas available. The Sun's stellar wind had strengthened, beginning to clear the nebula. As a result, Saturn captured less gas than Jupiter, reaching only 95 Earth masses compared to Jupiter's 318. This difference in mass led to profound differences in the planet's internal structures and evolution. Saturn's composition differs subtly, but importantly, from Jupiter's. While both are dominated by hydrogen and helium, Saturn is more enriched in heavy elements relative to its total mass. Saturn contains perhaps 25 to 30 Earth masses of elements heavier than helium, similar to Jupiter's heavy element content but in a less massive planet. This suggests Saturn's core makes up a larger fraction of its total mass. The internal structure of Saturn remains somewhat mysterious. Like Jupiter, it likely has a core of rock and ice, surrounded by layers of metallic and molecular hydrogen. However, recent measurements from the Cassini spacecraft suggest Saturn's core might be fuzzy rather than distinct, with heavy elements mixed into the surrounding hydrogen rather than separated into a discrete core. This could result from convective mixing over billions of years or reflect conditions during Saturn's formation. Saturn's lower mass means its interior pressure doesn't reach the extreme values found in Jupiter. The metallic hydrogen layer is smaller and forms deeper in the planet. This difference affects Saturn's magnetic field, which is much weaker than Jupiter's and almost perfectly aligned with the planet's rotation axis, unlike the tilted fields of most planets. One of Saturn's most puzzling features is its heat budget. Like Jupiter, Saturn emits more energy than it receives from the Sun, about 79% more. But unlike Jupiter, which is still cooling from its formation, Saturn's extra heat likely comes from a different source. As Saturn cools, helium condenses from the hydrogen-helium mixture in the upper atmosphere and rains toward the core. This helium rain releases gravitational energy, providing Saturn's extra heat. Saturn's atmosphere displays banded patterns similar to Jupiter's but more subtle, masked by a high-altitude haze. This haze, composed of ammonia ice crystals and complex hydrocarbons created by ultraviolet radiation, gives Saturn its distinctive pale gold colour. Beneath this haze, Saturn's atmosphere is surprisingly dynamic, with winds reaching 1,800 kilometers per hour, the fastest in the solar system. Every 30 Earth years or so, Saturn produces a spectacular atmospheric display, a great white spot. These enormous storms, comparable in size to Earth, appear in Saturn's northern hemisphere during summer. They begin as small bright spots but quickly expand, eventually wrapping entirely around the planet. The 2010 Great White Spot, observed by Cassini, grew to encircle Saturn within months, creating a planet-encircling storm system. At Saturn's north pole lies one of the solar system's most geometric mysteries, a hexagonal jet stream. This six-sided pattern, large enough to fit 4 Earths inside, has persisted for at least 40 years. The hexagon forms from the interaction of different wind speeds at different latitudes, creating a standing wave pattern. At the hexagon's centre spins a hurricane-like vortex with wind speeds of 500 kilometers per hour. Saturn's most distinctive feature, its ring system, tells a complex story of creation and destruction. The rings consist of countless particles, ranging from tiny dust grains to house-sized boulders, all orbiting Saturn independently. Despite their appearance, the rings are remarkably thin, typically only about 10 meters thick while spanning up to 282,000 kilometers in diameter. The ring particles are almost pure water ice, with trace amounts of rocky material and organic compounds. Their high reflectivity makes them visible from Earth with even a small telescope. The total mass of the rings equals about half that of Saturn's moon Mimas, far less than might be expected from their dramatic appearance. The origin of Saturn's rings remains debated. One theory suggests they formed from the destruction of a moon that wandered too close to Saturn and was torn apart by tidal forces. Another proposes they are remnants of the original material that formed Saturn, prevented from coalescing into moons by Saturn's gravity. Recent evidence suggests the rings might be relatively young, perhaps only 100 million years old, constantly renewed by the destruction of small moons. The rings divide into several distinct sections, separated by gaps where gravitational resonances with Saturn's moons clear out particles. The Cassini division, the most prominent gap, is maintained by a 2.1 resonance with the moon Mimas. Particles orbiting in this gap complete 2 orbits for every 1 orbit of Mimas, receiving regular gravitational tugs that eject them. Within the broad ring categories lie thousands of individual ringlets, density waves, and other structures. Spiral density waves, similar to those in galaxies but on a much smaller scale, propagate through the rings. Spoke features, radial markings that appear and disappear over hours, form from electrostatically levitated dust particles. Propeller-shaped gaps mark where small moonlets, too small to fully clear their orbits, create local disturbances. Some ring particles clump together temporarily, forming ephemeral structures that constantly form and dissolve. These clumps can grow to several hundred meters across before tidal forces tear them apart. This ongoing process of accretion and destruction prevents the ring particles from forming permanent moons within the main ring system. Saturn's moon system rivals Jupiter's in complexity and exceeds it in diversity. From tiny shepherd moons that maintain ring structures to planet-sized Titan with its thick atmosphere, Saturn's 62 confirmed moons present a bewildering variety of worlds. Each tells part of the story of Saturn system formation and evolution. Titan, Saturn's largest moon and the solar system's second largest, deserves special consideration. Larger than Mercury and the only moon with a substantial atmosphere, Titan resembles Earth in surprising ways. Its nitrogen-dominated atmosphere, denser than Earth's, hosts complex chemistry that produces organic compounds raining onto the surface. Beneath Titan's orange haze lies a landscape shaped by processes both familiar and alien. Rivers, lakes and seas cover parts of the surface, but they're filled with liquid methane and ethane rather than water. Rain falls from clouds, erodes channels, and pools in low-lying areas, creating a methane cycle analogous to Earth's water cycle. The largest seas, Kraken Mare and Leguia Mar, rival North America's Great Lakes in size. Titan's surface temperature of 94 Kelvin makes water ice behave like rock, forming mountains and canyons. Cryovolcanoes may erupt water and ammonia instead of molten rock. Beneath the icy crust lies a global ocean of liquid water, possibly habitable despite the frigid surface conditions. This subsurface ocean, kept liquid by tidal heating and the antifreeze effects of ammonia, might harbour exotic forms of life. Enceladus, a medium-sized moon only 500 kilometres across, has become one of the most exciting destinations in the solar system. From its south pole, geysers spray water vapor and ice particles hundreds of kilometers into space. These geysers, fed by a global ocean beneath the icy crust, create Saturn's diffuse E-ring and make Enceladus one of the most geologically active bodies in the solar system. The Cassini spacecraft flew through Enceladus's plumes, directly sampling material from its subsurface ocean. The results were remarkable. The ocean is salty, contains organic compounds, and has hydrothermal vents on its floor. These conditions resemble those near Earth's deep-sea vents, where life might have originated. Enceladus offers perhaps the most accessible habitable environment beyond Earth. Iapetus presents one of the solar system's strangest appearances, with one hemisphere bright as snow and the other dark as coal. This dramatic dichotomy results from Iapetus sweeping up dark material, likely from outer moon Phoebe, on its leading hemisphere. The dark material absorbs more sunlight, causing ice to sublimate and concentrate the dark material further. Iapetus also features an enigmatic equatorial ridge, 20 kilometers high in places, that gives it a walnut-like appearance. Mimas, the innermost of Saturn's major moons, bears an enormous impact crater named Herschel that makes it resemble the Death Star from Star Wars. This crater, 130 kilometers across on a moon only 400 kilometers in diameter, represents an impact that nearly destroyed Mimas. The moon's low density suggests it consists primarily of water ice with only a small rocky core. Hyperion, an irregularly shaped moon resembling a sponge, tumbles chaotically through space. Its rotation is unpredictable, changing orientation randomly over timescales of weeks. The moon's low density and high porosity suggest its largely empty space, perhaps the remnant of a larger body that lost most of its mass to impacts. Phoebe orbits Saturn backward in a distant, inclined orbit, suggesting it's a captured object from the Kuiper Belt. Its dark surface and primitive composition provide a sample of the outer solar system brought into Saturn's realm. Phoebe's dust, spiraling inward under solar radiation pressure, creates a vast, diffuse ring discovered only in 2009. Saturn's smaller moons include shepherd satellites that maintain ring edges, co-orbital moons that share the same orbit, and Trojan moons that share orbits with larger satellites. Pan, orbiting within the Encke Gap, has swept up ring material onto its equator, giving it a distinctive flying saucer shape. Prometheus and Pandora shepherd the narrow F-ring, though their gravitational influences create complex, ever-changing structures. Beyond the realm of the gas giants in the cold outer reaches of our solar system orbit two worlds fundamentally different from Jupiter and Saturn. Uranus and Neptune, the ice giants, formed under conditions and through processes that set them apart from their larger cousins. Their stories reveal the complex dynamics that shape the outer solar system and continue to influence it today. Uranus, orbiting at 19 astronomical units from the Sun, presents immediate mysteries. The planet lies on its side, tilted 98 degrees from vertical, essentially rolling along its orbital path rather than spinning upright. This extreme tilt affects everything about Uranus, from its seasons, each lasting 21 Earth years, to its magnetic field and ring system. The formation of Uranus began much like Jupiter and Saturn, with the accumulation of planetesimals in the cold outer disk. However, at Uranus's distance, the process proceeded much more slowly. The lower density of material and longer orbital periods meant collisions between planetesimals occurred less frequently. While Jupiter's core might have formed in 1 million years, Uranus's core probably took 10 million years or more to reach sufficient mass for gas accretion. By the time Uranus's core grew massive enough to capture gas from the nebula, much of that gas had already dissipated. The Sun's stellar wind had strengthened, and Jupiter and Saturn had consumed vast quantities of the available hydrogen and helium. As a result, Uranus captured a much smaller gas envelope relative to its core mass. The planet's final mass, 14.5 Earth masses, makes it the solar system's third largest planet, but only about 5% of Jupiter's mass. Uranus's composition reflects this formation history. Unlike Jupiter and Saturn, which are mostly hydrogen and helium, Uranus consists primarily of what planetary scientists call ices, water, methane, and ammonia. These compounds, solid in the cold outer solar system but fluid under pressure inside Uranus, make up perhaps 80% of the planet's mass. The remaining 20% divides between a rocky core and a hydrogen-helium envelope. The internal structure of Uranus differs markedly from the gas giants. Instead of distinct layers, Uranus likely has a more gradual transition from its small rocky core through a massive ice mantle to its atmosphere. The ice mantle isn't solid ice as we know it, but a hot, dense fluid under pressures millions of times greater than Earth's atmosphere. Under these conditions, water, methane, and ammonia form an electrically conductive ionic fluid, sometimes called a water-ammonia ocean. This internal ocean generates Uranus's magnetic field through convection, but the field is unlike any other in the solar system. Instead of aligning roughly with the planet's rotation axis, Uranus's magnetic field tilts 60 degrees and offsets from the planet's centre by about a third of Uranus's radius. This suggests the magnetic field originates in the ice mantle rather than the core, possibly from convection in a thin shell within the mantle. The cause of Uranus's extreme axial tilt remains one of the solar system's great mysteries. The leading theory involves a catastrophic collision early in Uranus's history. A body perhaps twice Earth's mass might have struck Uranus off-centre, knocking it onto its side. This impact would need to occur after Uranus formed its regular satellite system, but before that system could be disrupted. Alternatively, gravitational interactions with Saturn and Jupiter during planetary migration might have gradually tilted Uranus, though this seems less likely to produce such an extreme tilt. Uranus's atmosphere, though comprising only about 20% of its mass, extends for thousands of kilometres. Methane in the atmosphere absorbs red light and reflects blue-green, giving Uranus its distinctive colour. The atmosphere appears remarkably featureless in visible light, with only subtle banding and occasional clouds visible. This bland appearance masks complex atmospheric dynamics driven by Uranus's unusual seasons and internal heat flow. Unlike every other planet, Uranus emits almost no excess heat, radiating only about 6% more energy than it receives from the Sun. This suggests Uranus either formed with less initial heat, lost its heat more efficiently, or experienced an event that disrupted its internal heat flow. The hypothetical impact that tilted Uranus might have caused it to lose much of its primordial heat, leaving it unusually cold inside. Uranus's ring system, discovered in 1977, consists of 13 narrow rings vastly different from Saturn's broad, bright rings. The rings contain dark material, possibly organic compounds altered by radiation, making them nearly invisible except when backlit by the Sun. The narrowness of the rings, some only kilometres wide, requires shepherd moons to maintain their structure, though not all shepherds have been identified. The moon system of Uranus includes 27 known satellites, from tiny inner moons to 5 major moons comparable to Saturn's medium-sized satellites. The major moons, Miranda, Ariel, Umbriel, Titania and Oberon, likely formed from a disk of material orbiting Uranus after the hypothetical impact that tilted the planet. Their compositions, roughly half ice and half rock, reflect formation in Uranus's cold environment. Miranda, the innermost and smallest major moon, displays the most bizarre geology in the solar system. Its surface combines old, heavily cratered terrain with young, complex regions featuring ridges, scarps, and chevron-shaped formations. One cliff, Verona Rupes, drops 20 kilometers, the tallest known cliff in the solar system. These features suggest Miranda was catastrophically disrupted and reassembled, or experienced extreme tidal heating in the past. Neptune, at 30 astronomical units from the Sun, is the solar system's outermost major planet. Nearly identical in size to Uranus, but about 18% more massive, Neptune is the densest of the giant planets. This higher density suggests Neptune contains a larger fraction of rock and less ice than Uranus, though both are classified as ice giants. Neptune's formation poses particular challenges for planetary scientists. At its current distance, Neptune couldn't have formed within the age of the solar system. The orbital timescales are simply too long for sufficient accretion. This suggests Neptune formed closer to the Sun, perhaps between Saturn and Uranus, then migrated outward to its current position. This migration, likely caused by gravitational interactions with Jupiter and Saturn, would have dramatically reshaped the outer solar system. Despite receiving only 40% as much sunlight as Uranus, Neptune appears more active and dynamic. The planet radiates about 2.6 times more energy than it receives from the Sun, the highest ratio of any planet. This internal heat, possibly from continued gravitational contraction or phase changes in the interior, drives the solar system's fastest winds and most dynamic weather. Neptune's atmosphere displays prominent features absent on Uranus. The Great Dark Spot, discovered by Voyager 2 in 1989, was an Earth-sized storm similar to Jupiter's Great Red Spot. However, when the Hubble Space Telescope observed Neptune 5 years later, this spot had vanished, and a new dark spot had appeared in the northern hemisphere. These transient storms, along with bright clouds of methane ice crystals, reveal Neptune's dynamic atmosphere. Winds on Neptune reach supersonic speeds of 2,100 kilometers per hour, nearly breaking the sound barrier in Neptune's atmosphere. Mysteriously, these winds blow retrograde, opposite to the planet's rotation, at the equator, but become prograde at higher latitudes. The energy source for these powerful winds, given Neptune's distance from the Sun and relatively weak solar heating, must come primarily from internal heat. Neptune's magnetic field, like Uranus's, tilts significantly from the rotation axis, about 47 degrees, and offsets from the planet's centre. This similarity between Neptune and Uranus suggests their tilted, offset magnetic fields result from their internal structure rather than catastrophic events. The fields likely generate in a thin convecting shell within the ice mantle rather than in the core, producing their unusual configurations. Neptune's ring system consists of 5 main rings, with unusual bright arc features in the outermost Adam's ring. These arcs, named Liberty, Equality, Fraternity, and Courage, concentrate ring particles in segments rather than spreading uniformly around the ring. The moon Galatea gravitationally confines these arcs, though they appear to be evolving and may disappear within centuries. Triton, Neptune's largest moon, and the solar system's 7th largest satellite, orbits backward relative to Neptune's rotation. This retrograde orbit immediately identifies Triton as a captured object rather than a moon that formed alongside Neptune. Triton likely originated in the Kuiper Belt, the region of icy bodies beyond Neptune, and was gravitationally captured during a close encounter with Neptune. The capture process must have been violent and complex. A lone Triton passing Neptune would simply be deflected, not captured. Triton might have been part of a binary system, with Neptune's gravity separating the pair and capturing Triton while ejecting its companion. Alternatively, collisions with existing moons or aerodynamic drag in Neptune's extended atmosphere during the early solar system might have enabled capture. After capture, Triton's initial orbit would have been highly elliptical. Tidal forces from Neptune gradually circularized this orbit while heating Triton's interior tremendously. This tidal heating likely melted Triton completely, allowing it to differentiate into a rocky core, ice mantle, and possibly a subsurface ocean. The energy dissipated during orbital circularization would have disrupted or ejected Neptune's original satellite system, explaining why Neptune has fewer moons than the other giant planets. Today, Triton orbits in a nearly perfect circle, but tidal forces continue to affect it. Neptune's gravity gradually slows Triton's orbit, causing it to spiral inward. In about 3.6 billion years, Triton will reach Neptune's Roche limit, the distance at which tidal forces overcome Triton's self-gravity. The Moon will be torn apart, possibly creating a spectacular ring system, far surpassing Saturn's. Triton's surface presents a fascinating frozen landscape. With a temperature of 38 Kelvin, it's one of the coldest places in the solar system. The surface consists primarily of nitrogen ice, with traces of methane and carbon monoxide. Like Pluto, which it closely resembles, Triton has a thin nitrogen atmosphere that freezes and sublimes with seasonal changes. Geysers on Triton, discovered by Voyager 2, erupt nitrogen gas and dark particles up to 8 kilometers high. These geysers, powered by solar heating of subsurface nitrogen ice, despite the incredible distance from the Sun, demonstrate that geological activity can occur even on the coldest worlds. Dark streaks on Triton's surface mark where geyser particles have settled, carried downwind by Triton's thin atmosphere. The capture of Triton and the migration of Neptune had profound effects on the Kuiper Belt. As Neptune moved outward, it scattered countless small bodies, depleting the Kuiper Belt of much of its original mass. Some scattered objects were flung inward, potentially contributing to the late heavy bombardment that scarred the inner planets. Others were pushed into resonant orbits with Neptune, creating the various dynamical populations we observe in the Kuiper Belt today. Beyond Neptune lies a vast realm of icy bodies left over from the solar system's formation. The Kuiper Belt, extending from Neptune's orbit at 30 astronomical units to roughly 50 astronomical units from the Sun, contains hundreds of thousands of objects larger than 100 kilometers across and trillions of smaller bodies. This region preserves a record of the solar system's early history and continues to supply comets that occasionally visit the inner solar system. The story of the Kuiper Belt begins with the solar system's formation, when the protoplanetary disk extended far beyond Neptune's current orbit. In these frigid regions, temperatures never exceeded 50 Kelvin, cold enough for even volatile compounds like nitrogen, methane, and carbon monoxide to condense as ices. The solid materials available for planet formation included not just water ice and rock, but these exotic ices that would sublimate instantly in the inner solar system. Initially, this region contained enough material to form several Neptune-sized planets. The surface density of solids followed a smooth continuation of the trend from the inner solar system, with perhaps 10 Earth masses of material spread between 30 and 50 astronomical units. Planetesimals formed and began growing, following the same processes occurring closer to the Sun, but at a much slower pace due to the longer orbital periods and lower collision velocities. However, planet formation in this region never completed. The migration of Neptune through this zone, whether gradual or sudden, disrupted the orderly growth of bodies. Neptune's gravity scattered most planetesimals, ejecting some from the solar system entirely, sending others inward toward the Sun, and leaving only a small fraction in stable orbits. The current Kuiper belt contains only about 1% of its original mass, the survivors of this dramatic depletion. Pluto, discovered in 1930 and reclassified as a dwarf planet in 2006, exemplifies the largest class of Kuiper belt objects. At 2,370 kilometers in diameter, Pluto is smaller than Earth's moon, but large enough that gravity has pulled it into a spherical shape. Its composition, roughly 70% rock and 30% ice, reflects formation in the cold outer solar system, where both materials were plentiful. Pluto's orbit tells a story of gravitational interactions with Neptune. Locked in a 3-2 resonance with Neptune, Pluto completes 2 orbits for every 3 of Neptune's. This resonance protects Pluto from close encounters with Neptune, despite their crossing orbits. The resonance likely captured Pluto during Neptune's outward migration, sweeping Pluto up as Neptune moved through the primordial Kuiper belt. The New Horizons spacecraft's 2015 flyby revolutionized our understanding of Pluto, revealing an unexpectedly complex and active world. Instead of the dead, cratered surface many expected, Pluto displays vast nitrogen ice plains, water ice mountains as tall as the Rockies, and evidence of recent geological activity. The heart-shaped Tombor Regio, a bright nitrogen ice plain, shows no impact craters, indicating its surface is less than 10 million years old. This geological activity on such a cold, distant world challenges our understanding of planetary processes. Convection within the nitrogen ice, driven by Pluto's feeble internal heat, creates polygon patterns similar to those in Earth's polar regions, but on a vastly larger scale. Glaciers of nitrogen ice flow into basins, and exotic ices behave like rock and liquid water do on Earth. Some scientists speculate Pluto might harbour a subsurface ocean, kept liquid by ammonia antifreeze and the insulating properties of a gas hydrate layer. Pluto's largest moon, Charon, nearly half Pluto's size, makes the Pluto-Charon system almost a double planet. The two bodies orbit their mutual centre of mass, which lies in space between them. Charon likely formed from debris ejected when a large body collided with proto-Pluto, similar to how Earth's moon formed. This giant impact might explain the high angular momentum of the system and the similar compositions of Pluto and Charon. Charon's surface differs dramatically from Pluto's, dominated by water ice rather than nitrogen. A vast canyon system, longer and deeper than the Grand Canyon, splits Charon's surface, possibly formed when a subsurface ocean froze and expanded. The red-tinged North Pole, informally called Mordor Macula, consists of organic compounds captured from Pluto's escaping atmosphere and processed by solar radiation. 4 tiny moons orbit beyond Charon: Styx, Nix, Kerberos, and Hydra. These irregular bodies, ranging from 10 to 50 kilometers across, tumble chaotically through space rather than rotating synchronously. They likely formed from debris of the same impact that created Charon, representing the small fraction of material that didn't coalesce into the larger moon. Eris, discovered in 2005, catalyzed Pluto's reclassification by demonstrating that Pluto wasn't unique. Slightly smaller but more massive than Pluto, Eris orbits far beyond the classical Kuiper belt in a region called the scattered disk. Its highly elliptical orbit, ranging from 38 to 98 astronomical units from the Sun, suggests a violent gravitational encounter with Neptune in the past. Eris's surface, covered in methane ice, appears almost pure white, reflecting 96% of sunlight. This fresh ice surface likely results from methane sublimating when Eris approaches the Sun, then freezing out as fresh snow when it recedes. At Eris's current distance, near aphelion, its atmosphere has completely frozen onto the surface, creating a pristine, icy coating. Makemake, another large dwarf planet, displays a surface covered in methane and ethane ices, processed by cosmic radiation into complex organic compounds called tholins. These reddish-brown materials give Makemake its characteristic colour. Unlike Pluto, Makemake appears to lack a substantial atmosphere, though one might develop when it approaches perihelion. Haumea presents one of the solar system's most unusual shapes. Rapid rotation, completing a spin in just 4 hours, has stretched Haumea into an ellipsoid twice as long as it is wide. This football-shaped dwarf planet likely suffered a glancing collision that spun it up and created its 2 small moons, Hikiaka and Namaka. The collision also produced a family of smaller Kuiper belt objects with similar orbits and compositions. The Kuiper belt divides into several distinct populations based on orbital characteristics. The classical Kuiper belt objects, or cubewanos, orbit in relatively circular orbits between 40 and 48 astronomical units, undisturbed by Neptune. These objects preserve the most pristine record of the outer solar system's original architecture. The resonant populations occupy orbits in various mean motion resonances with Neptune. The 3-2 resonance, home to Pluto and dozens of other Plutinos, is the most populated. Other resonances, including 2.1, 5.2 and 4.3, contain their own populations. These resonant objects were likely captured during Neptune's migration, swept up as the planet moved outward. The scattered disk extends beyond the classical Kuiper belt, containing objects with highly elliptical and often inclined orbits. These bodies experienced close encounters with Neptune that flung them onto their current paths. Some scattered disk objects travel hundreds of astronomical units from the Sun, spending most of their time in the frigid darkness, far from any planetary influence. Centaurs, which orbit between Jupiter and Neptune, represent Kuiper belt objects transitioning inward. Gravitational perturbations from the giant planets scattered these bodies from the Kuiper belt onto unstable orbits crossing planetary paths. Over millions of years, centaurs will either collide with planets, be ejected from the solar system, or evolve into short-period comets. The composition of Kuiper belt objects varies considerably, reflecting different formation locations and evolutionary histories. Some are primarily rock with ice mantles, others are more ice-rich throughout. Surface compositions range from nearly pure water ice to complex mixtures of methane, ammonia, carbon dioxide, and organic compounds. This diversity provides clues about temperature and chemical conditions in the early outer solar system. Many Kuiper belt objects are binaries, with 2 bodies orbiting their mutual centre of mass. The high fraction of binaries, perhaps 30% among the largest objects, suggests gentle formation conditions that allowed loosely bound pairs to survive. These binaries provide valuable information about the masses and densities of Kuiper belt objects, measurements difficult to obtain otherwise. Contact binaries, where 2 bodies rest against each other, are also common. Arrokoth, visited by New Horizons in 2019, consists of 2 lobes that gently merged at speeds of just a few meters per second. This pristine contact binary preserves the accretion process that built larger bodies from smaller components in the early solar system. The colours of Kuiper belt objects range from neutral grey to deep red, determined by their surface compositions and processing history. Cosmic rays and solar ultraviolet radiation chemically alter surface ices, creating complex organic compounds. The reddest objects typically have surfaces rich in these processed organics, while greyer objects might have fresher ice exposed by recent impacts or geological activity. Far beyond the Kuiper belt, extending perhaps a quarter of the way to the nearest star, lies the most distant realm of our solar system, the Oort cloud. This vast spherical shell of icy bodies reaching from roughly 2,000 to 100,000 astronomical units from the Sun marks the gravitational boundary of our solar system. Here, in the deep freeze of interstellar space, trillions of comets orbit in slow, centuries-long paths, occasionally falling inward to become the spectacular comets we observe from Earth. The Oort cloud's existence was first proposed by Dutch astronomer Jan Oort in 1950 to explain the origin of long-period comets. These comets arrive from all directions, not confined to the plane of the solar system like planets and Kuiper belt objects. Their orbits suggest an origin in a spherical distribution of bodies surrounding the solar system at vast distances. The formation of the Oort cloud tells a story of planetary migration and gravitational sculpting. The bodies now in the Oort cloud didn't form there. At such distances, the protoplanetary disk was too sparse for accretion. Instead, these objects formed much closer to the Sun, in the region of the giant planets, as icy planetesimals similar to those that built the cores of Jupiter, Saturn, Uranus, and Neptune. As the giant planets grew and migrated, their gravity scattered nearby planetesimals onto highly elliptical orbits. Most scattered bodies were ejected from the solar system entirely, achieving escape velocity and disappearing into interstellar space. Others struck the Sun or planets, but a small fraction entered orbits that took them far from the Sun while remaining gravitationally bound. At these enormous distances, the Sun's gravity weakens to the point where external forces become significant. The gentle gravitational pull of passing stars, the tidal force of the Milky Way galaxy itself, and encounters with giant molecular clouds gradually modified these orbits. Over millions of years, these perturbations raised the perihelia of scattered planetesimals, preventing them from returning to the planetary region. The orbits also became more randomly oriented, creating the spherical distribution we call the Oort cloud. The Oort cloud likely contains two distinct regions. The inner Oort cloud, or Hills cloud, extends from about 2,000 to 20,000 astronomical units. This donut-shaped region remains somewhat flattened along the solar system's plane, reflecting its origin from scattered disk objects. The outer Oort cloud, from 20,000 to perhaps 100,000 astronomical units or more, forms a roughly spherical shell with orbits oriented in all directions. Estimating the Oort cloud's population requires extrapolating from the few comets we observe. Scientists estimate the cloud contains between 100 billion and 2 trillion bodies larger than a kilometre across, with a combined mass of perhaps 5 to 20 Earth masses. Most of this mass resides in the largest bodies, which might include objects as large as dwarf planets, though none have been directly observed at such distances. The composition of Oort cloud objects likely resembles that of Kuiper belt objects and cometary nuclei, mixtures of water ice, frozen gases like carbon dioxide and methane, rocky material, and organic compounds. Having spent billions of years at temperatures just a few degrees above absolute zero, these bodies preserve the primordial composition of the outer protoplanetary disk. Comets enter the inner solar system when gravitational perturbations alter their orbits. A passing star might disturb the Oort cloud, sending a shower of comets inward. The solar system's passage through the galaxy's spiral arms, occurring roughly every 100 million years, increases the rate of stellar encounters. Some scientists have proposed correlations between these passages and mass extinction events on Earth, though this remains controversial. The Sun's vertical oscillation through the galactic plane also affects the Oort cloud. Every 30 to 40 million years, the solar system passes through the denser midplane of the galaxy, where encounters with stars and molecular clouds are more frequent. These passages might trigger comet showers lasting millions of years. Once perturbed onto an inbound trajectory, an Oort cloud comet begins a journey that might take millions of years. As it falls toward the Sun, the comet accelerates under solar gravity. Initially invisible and unknown, the comet remains frozen solid until it approaches the outer planets. As it continues inward, solar heating begins to sublimate frozen gases, creating the characteristic coma and tail that make comets spectacular. Long-period comets from the Oort cloud provide our only direct samples of this distant region. When these comets approach the Sun, they release pristine material unchanged since the solar system's formation. Spacecraft missions to comets, like Rosetta's visit to Comet 67P Churyumov-Gerasimenko, reveal their structure and composition. Though 67P is a short-period comet from the Kuiper belt rather than the Oort cloud. The boundary of the Oort cloud marks the limit of the Sun's gravitational dominance. Beyond about 100,000 astronomical units, roughly 1.6 light-years, the gravitational field of other stars and the galaxy become stronger than the Sun's. Objects beyond this distance cannot remain bound to our solar system. Sedna, discovered in 2003, occupies a peculiar orbit that might link the scattered disk to the inner Oort cloud. With a perihelion of 76 astronomical units and a phelion of 937 astronomical units, Sedna never comes close enough to Neptune to have been scattered by that planet. Its orbit suggests either perturbation by a passing star, interaction with a now ejected planet, or formation in a star cluster where stellar encounters were common. The discovery of additional objects with Sedna-like orbits has led to proposals of an undiscovered Planet 9 in the outer solar system. This hypothetical planet, perhaps 10 Earth masses, might orbit at 400 to 800 astronomical units, shepherding these distant objects into aligned orbits. The search for Planet 9 continues, representing one of the most exciting frontiers in planetary science. As we look forward to billions of years, the story of our solar system continues with slow but inexorable changes that will ultimately transform every world we've come to know. The future unfolds across timescales so vast that all of human history represents less than a heartbeat. Yet the physical processes driving these changes operate continuously, moment by moment, gradually reshaping our cosmic neighbourhood. The Sun, the engine driving all activity in our solar system, continues its steady evolution along the main sequence. Deep in its core, hydrogen fuses into helium at a rate of 600 million tons per second, slowly altering the Sun's composition and structure. As helium accumulates in the core, the Sun must burn hydrogen slightly faster to maintain equilibrium against gravity. This causes a gradual brightening, about 1% every 100 million years. This slow brightening has profound implications for the planets, particularly Earth. In about 500 million years, the Sun will be roughly 5% brighter than today. This additional energy will enhance the weathering of silicate rocks, which removes carbon dioxide from the atmosphere. As CO2 levels drop below the threshold for photosynthesis, complex plant life will begin to disappear. The collapse of the food chain will follow, marking the beginning of the end for Earth's biosphere as we know it. By 1 billion years from now, the Sun's luminosity will have increased by about 10%. This extra heat will trigger a runaway greenhouse effect on Earth. As temperatures rise, more water vapour enters the atmosphere. Since water vapour is itself a greenhouse gas, this creates a positive feedback loop. The oceans will begin to evaporate, and Earth will start its transformation into a world more like Venus. The loss of Earth's oceans will occur through the same process that dried out Venus billions of years ago. In the upper atmosphere, ultraviolet radiation will break apart water molecules. Hydrogen, the lightest element, will escape to space, while oxygen will react with surface rocks or accumulate in the atmosphere. Within a few 100 million years, Earth's oceans will be gone forever. Mars, ironically, might become more hospitable as the sun brightens. The increased solar energy could thicken Mars's atmosphere through sublimation of frozen CO2 at the poles. While Mars will never recover the thick atmosphere it may have had in its youth, it might briefly experience conditions allowing liquid water on its surface again, at least in certain regions and seasons. The outer planets will also feel the effects of the brightening sun, though less dramatically. The boundaries of the habitable zone, the region where liquid water can exist on planetary surfaces, will shift outward. Some models suggest that in about 1 billion years, the moons of Jupiter and Saturn might experience conditions suitable for life, at least temporarily. Europa's subsurface ocean, currently locked beneath kilometres of ice, might break through to the surface. Enceladus's geysers could become more active. Titan's methane lakes will evaporate, but its water ice crust might begin to melt, creating a water ocean beneath its organic-rich atmosphere. These moons could become the solar system's last refuges for life, as the inner planets become uninhabitable. The sun's evolution accelerates dramatically once it exhausts the hydrogen in its core about 5 billion years from now. With no fusion to provide outward pressure, the core will contract under gravity, heating up as it compresses. This heat will cause hydrogen in a shell around the inert helium core to begin fusing, providing the sun's energy. However, shell burning is less stable than core burning, causing the sun to expand and cool, becoming a red giant. The sun's transformation into a red giant will be catastrophic for the inner solar system. Over a period of about 1 billion years, the sun will expand to roughly 200 times its current diameter. Its surface will cool to about 3000 Kelvin, glowing red rather than white. The sun's luminosity will increase to roughly 2000 times its current output, though this energy will be spread over a much larger surface area. Mercury will be the first casualty. As the sun expands, it will engulf Mercury entirely. The small planet will spiral inward through the sun's outer atmosphere, friction heating it until it vaporizes completely. Mercury's atoms will become part of the sun's atmosphere, ending the innermost planet's 5 billion year existence. Venus faces a similar fate. As the sun continues to expand, it will reach Venus's orbit. The planet might survive slightly longer than Mercury due to its greater mass, but it too will eventually spiral inward and vaporize. The thick atmosphere that defines Venus today will be stripped away first, followed by the vaporization of its surface rocks. Earth's fate remains uncertain. Models of stellar evolution suggest the sun will expand to roughly 1.1 to 1.2 astronomical units, just reaching or slightly exceeding Earth's current orbit. However, as the sun loses mass through its stellar wind, which will be much stronger during the red giant phase, the planet's orbits will expand. Earth might migrate outward just enough to avoid being engulfed. Even if Earth escapes direct engulfment, it will be transformed beyond recognition. The intense heat will vaporize any remaining water and melt the surface rocks. Earth might develop a temporary atmosphere of vaporized rock, with silicon and metal vapors creating exotic clouds. The surface will glow red hot, and any evidence of life or human civilization will be completely erased. During the red giant phase, the habitable zone will shift dramatically outward. Mars will be scorched, its polar caps long since vaporized. The asteroid belt will experience temperatures that could melt many asteroids. But farther out, interesting changes will occur. Jupiter's moons will experience a brief spring. Europa's ice shell will melt completely, exposing its ocean to space. Ganymede and Callisto might also develop surface oceans. These water worlds could theoretically support life, though the red giant phase won't last long enough for complex life to evolve from scratch. Saturn's moon, Titan, will undergo dramatic changes. Its methane will be destroyed by the intense ultraviolet radiation from the red giant sun. The water ice that forms much of its crust will begin to melt. For perhaps a few 100 million years, Titan might have liquid water on its surface, with its thick nitrogen atmosphere creating a substantial greenhouse effect. Even the Kuiper belt will feel the red giant sun's influence. Objects like Pluto will warm dramatically, their nitrogen and methane ices sublimating to create temporary atmospheres. Some Kuiper belt objects might develop subsurface oceans as their ice mantles warm. The frozen outer solar system will briefly thaw. The red giant phase won't last forever. After about 1 billion years, the helium accumulated in the sun's core will reach temperatures and pressures sufficient for helium fusion. This helium flash will occur suddenly, with helium fusing into carbon and oxygen. The energy release will cause the sun to contract somewhat and burn more stably for a brief period. This helium-burning phase lasts only about 100 million years. The sun will exhaust its helium relatively quickly, leading to another expansion phase. This time, the sun becomes an asymptotic giant branch star, even larger and more luminous than before. Complex nuclear processes create heavier elements, up to iron, and the sun begins to pulsate, varying in brightness over periods of years to decades. During this phase, the sun loses mass rapidly through an enhanced stellar wind. Perhaps half the sun's mass will be ejected into space, forming an expanding shell of gas around the dying star. This mass loss causes the planet's orbits to expand further. Earth, if it survived the first red giant phase, will orbit at perhaps 1.5 astronomical units. Mars will be pushed out to 3 astronomical units or more. The sun's final transformation begins when it can no longer sustain fusion. With no energy source to support it against gravity, the sun will contract rapidly. However, it lacks sufficient mass to ignite carbon fusion, which would require a star at least 8 times the sun's mass. Instead, the sun's core will collapse into a white dwarf, an Earth-sized object containing about half the sun's original mass. The collapse happens quickly by astronomical standards, over just a few thousand years. The sun's outer layers, no longer held by gravity, will be ejected into space as a planetary nebula. This beautiful shell of glowing gas, ionized by the hot white dwarf at its center, will expand outward at dozens of kilometers per second. The nebula will be visible from thousands of light years away, briefly making our dying sun one of the prettier objects in the galaxy. The white dwarf sun will be extraordinarily dense, with a teaspoon of its material weighing as much as a car. Its surface temperature will initially exceed 100,000 Kelvin, making it appear blue-white despite being only about Earth's size. The white dwarf's intense gravity, 300,000 times Earth's surface gravity, will create bizarre effects. Light leaving its surface will be gravitationally redshifted, and space-time near the white dwarf will be measurably curved. The planets that survive will orbit much farther from the white dwarf sun due to the sun's mass loss. Earth, if it still exists, will orbit at roughly 2 astronomical units in a frozen wasteland. The white dwarf will provide negligible heat, with temperatures everywhere in the solar system falling to just a few degrees above absolute zero. The white dwarf sun will cool slowly over trillions of years. White dwarfs cool by radiation alone, with no internal energy source. The cooling rate depends on the white dwarf's composition and mass, but our sun will take about 1 billion years to cool to 20,000 Kelvin, still hotter than the current sun's surface. After 10 billion years, it will cool to 5,000 Kelvin, glowing a dim red. Eventually, after perhaps a quadrillion years, the white dwarf will cool to the temperature of the cosmic microwave background radiation. It will become a black dwarf, a cold, dark sphere of degenerate matter, invisible except for its gravitational influence. No black dwarfs exist yet anywhere in the universe, as the cosmos isn't old enough for any white dwarf to have cooled completely. The planet's ultimate fate depends on encounters with passing stars over immense timescales. As the solar system orbits the galaxy, stellar encounters will occasionally perturb the planet's orbits. Most encounters will be distant and have minimal effect, but over trillions of years, cumulative perturbations will destabilize the planetary system. Computer simulations suggest that within about 100 billion years, gravitational perturbations will likely eject most planets from the solar system. They'll become rogue planets, wandering through interstellar space forever. A few planets might spiral into the white dwarf sun, briefly causing it to flare as their material spreads across its surface. On even longer timescales, measured in 10-15 years or more, the planets themselves will begin to disintegrate. Quantum tunneling will cause protons in ordinary matter to spontaneously decay, though this theoretical process has never been observed and might not occur. If proton decay doesn't happen, the planets will instead slowly evaporate through quantum tunneling of their constituent atoms into space. The white dwarf sun faces its own eventual fate. Through quantum processes operating over unimaginable timescales, perhaps 1065 years, the white dwarf will undergo a phase transition to a ball of iron 56, the most stable atomic nucleus. Later still, over timescales of 10-1500 years, even this iron sphere will quantum tunnel into a black hole, which will then evaporate through Hawking radiation. These ultimate fates lie so far in the future that they're almost meaningless to contemplate. The universe itself will be unrecognizably different, with all stars extinguished, galaxies dispersed, and perhaps even the fundamental constants of physics changed through cosmic evolution. The story of our solar system will be long forgotten, its atoms dispersed throughout space or locked in stellar remnants. Yet the solar system's legacy extends beyond its physical components. The heavy elements forged in the sun and processed through planetary geology will be recycled into future generations of stars and planets. The organic molecules created in our solar system might seed life elsewhere. The gravitational waves from planetary orbits, though infinitesimally weak, propagate across the universe forever. In about 4 billion years, before the sun becomes a red giant, our galaxy will experience a dramatic transformation. The Andromeda Galaxy, currently approaching at 300,000 miles per hour, will collide and merge with the Milky Way. This galactic collision won't directly affect the solar system, as stars are too widely spaced to collide. However, gravitational perturbations during the merger could fling our solar system into a different galactic orbit, or even eject it into intergalactic space. If the solar system is ejected from the merged galaxy, it will drift through the cosmic void as an island universe unto itself. The planets will continue orbiting the dying sun, later the white dwarf, in perfect isolation. The night sky will be almost completely dark, with only distant galaxies visible as faint smudges. This lonely exile might actually preserve the solar system longer, avoiding disruptive stellar encounters. As we contemplate these vast timescales and dramatic transformations, it's worth remembering that our understanding of the far future remains uncertain. Dark energy, discovered only recently, might dramatically alter the universe's evolution. New physics beyond our current theories could change these predictions entirely. The solar system's ultimate fate might be stranger than we can currently imagine. The moons of the giant planets face their own evolutionary paths. Tidal forces continue to alter their orbits, with some moons spiraling inward toward destruction, while others migrate outward toward escape. Io's volcanic activity will eventually cease as tidal heating diminishes. Europa's ocean will freeze solid as radioactive heating fades. Titan's organic chemistry will continue until the Sun's red giant phase destroys its delicate molecules. The rings of the giant planets are temporary features on geological timescales. Saturn's magnificent rings might disappear within 300 million years, ground to dust by collisions and dispersed by radiation pressure and electromagnetic forces. The material will either fall into Saturn or be ejected from the system. Jupiter, Uranus, and Neptune's rings will similarly evolve and dissipate. New rings might form as moons are destroyed. When Triton reaches Neptune's Roche limit in 3 billion years, its destruction will create a ring system potentially rivaling Saturn's current rings. Mars's moon Phobos will meet a similar fate much sooner, perhaps in 50 million years, briefly giving Mars a ring system. The asteroid belt will gradually deplete through collisions and gravitational perturbations. Some asteroids will impact planets, delivering water and organic materials. Others will be ejected from the solar system or fall into the Sun. The belt will become sparser and sparser until only the largest, most stable asteroids remain. The Kuiper belt faces similar depletion, though on longer timescales due to the lower collision rates at greater distances. Gravitational perturbations from passing stars will occasionally scatter Kuiper belt objects inward as comets or outward into interstellar space. Over billions of years, the Kuiper belt will fade away, leaving only the most stable, resonant objects. Comets from the Oort cloud will continue falling into the inner solar system until the Sun's red giant phase disrupts their orbits. The stellar wind from the red giant Sun might blow away much of the Oort cloud, ending the age of comets. Any remaining Oort cloud objects will be scattered when passing stars disrupt their orbits over the following billions of years. As we reach the end of this vast journey through time, from the solar system's birth in a collapsing molecular cloud to its ultimate dissolution in the far future, we see a story of continuous change and transformation. Worlds have formed and evolved, life has potentially emerged and will eventually vanish, and the very structure of our cosmic neighbourhood has been reshaped repeatedly. The solar system's story is one of both creation and destruction, of brief moments of habitability in a largely hostile cosmos, and of the relentless march of physical processes operating across incomprehensible timescales. Every planet, moon, asteroid, and comet has its own unique history, shaped by its formation, evolution, and interactions with other bodies. From the scorched surface of Mercury to the frozen depths of the Kuiper belt, from the thick atmosphere of Venus to the thin wisp surrounding Pluto, from the volcanic fury of Io to the hidden oceans of Europa and Enceladus, our solar system presents a remarkable diversity of worlds and environments. Each tells part of the greater story, contributing to our understanding of planetary systems throughout the universe. This story connects us to the cosmos in profound ways. The atoms in our bodies were forged in the nuclear furnaces of dying stars, scattered through space in supernova explosions, incorporated into the molecular cloud that became our solar system, processed through planetary geology, and eventually assembled into living beings capable of contemplating their own origins. We live in a special time in the solar system's history. The Sun is stable and moderate in its energy output. Earth maintains conditions suitable for complex life. The giant planets shield us from many potential impactors. The arrangement of planets provides gravitational stability that has persisted for billions of years, allowing life to evolve from simple microbes to conscious beings capable of understanding their cosmic context. This moment of stability and habitability represents perhaps 1% of the solar system's total lifetime. For most of its history, our solar system has been or will be hostile to life as we know it. The early solar system was a chaos of colliding planetesimals and sterilizing impacts. The far future holds the death of the sun and the freezing or incineration of all worlds. We exist in a brief golden age between formation and destruction. Understanding the solar system's past and future gives us perspective on our place in the universe. We see that change is the only constant, that worlds can transform from habitable to hellish or frozen to temperate, that entire planets can be destroyed or ejected into darkness. This knowledge makes our living Earth all the more precious, a temporary oasis in space and time. The exploration of our solar system, through telescopes, spacecraft, and theoretical models, has revealed wonders beyond the imagination of previous generations. We've walked on the moon, driven rovers across Mars, flown through the geysers of Enceladus, and touched the atmosphere of the Sun. We've discovered oceans inside moons, rivers on Titan, and the heart-shaped plains of Pluto. Each discovery raises new questions. How did life begin on Earth, and does it exist elsewhere in our solar system? What determines whether a planet develops and maintains habitability? How common are planetary systems like ours in the galaxy? These questions drive continued exploration and research, pushing the boundaries of our knowledge and capabilities. The solar system also serves as our only accessible laboratory for understanding planetary processes throughout the universe. By studying the diversity of worlds in our own system, we can interpret observations of exoplanets orbiting distant stars. The geology of Mars helps us understand desert worlds everywhere. The atmospheric dynamics of Jupiter and Saturn provide insights into gas giants throughout the cosmos. As we prepare to venture beyond Earth, the solar system becomes not just an object of study, but a destination for human expansion. The Moon offers resources and a platform for deep space exploration. Mars presents the possibility of a second home for humanity. The asteroids contain vast mineral wealth. The moons of the outer planets harbour water and other resources essential for space settlements. Yet the solar system also reminds us of the fragility of habitable worlds. Venus shows us the devastation of a runaway greenhouse effect. Mars demonstrates how a planet can lose its atmosphere and water. These cautionary tales emphasize the importance of protecting Earth's environment and climate. We have no readily accessible backup planet if we damage this one beyond repair. The rhythms of the solar system, from the daily rotation of planets to the centuries-long orbits of comets, have shaped human culture and consciousness. Ancient civilizations tracked planetary motions and built monuments aligned with celestial events. The regular cycles of the moon became our calendar. The wandering of planets through the sky inspired mythology and eventually scientific revolution. Today, our relationship with the solar system grows ever more intimate. Weather satellites monitor Earth's climate. Communication satellites connect global civilization. Navigation satellites guide us with precision impossible just decades ago. Space telescopes reveal the universe beyond. Robotic explorers serve as our proxies, visiting worlds we cannot yet reach in person. The resources of the solar system could support civilization for millions of years. The asteroid belt alone contains enough iron to build space habitats, with combined surface areas thousands of times greater than Earth. The water ice in Jupiter's moons could support billions of people. The helium-3 in the lunar soil and gas giant atmospheres could power fusion reactors. These resources await only our ability to access and utilize them. But exploiting these resources requires wisdom to avoid the mistakes we've made on Earth. The solar system's pristine environments deserve protection even as we expand into space. The scientific value of untouched worlds must be balanced against resource extraction. International cooperation will be essential to prevent conflict over space resources and territory. The search for life within our solar system continues with increasing sophistication. Each potentially habitable environment receives scrutiny. The subsurface oceans of Europa and Enceladus, the methane lakes of Titan, the ancient river valleys of Mars, even the cloud layers of Venus, where temperatures and pressures might allow microbial life. The discovery of life beyond Earth, even simple microbes, would revolutionize our understanding of biology and our place in the universe. If life exists elsewhere in our solar system, it likely differs dramatically from Earth life. Organisms in Europa's dark ocean would never know sunlight. Life in Titan's hydrocarbon lakes would use liquid methane instead of water. Martian microbes would endure radiation levels lethal to Earth organisms. These alternative forms of life would expand our definition of habitability and guide our search for life around other stars. The solar system's small bodies, the asteroids and comets, preserve the most primitive materials from our system's formation. They're time capsules containing information about conditions in the protoplanetary disk. Some meteorites contain organic molecules and even amino acids, the building blocks of proteins. These discoveries suggest the ingredients for life were present throughout the early solar system and might have been delivered to Earth by impacting comets and asteroids. The boundary between our solar system and interstellar space continues to be explored. The Voyager spacecraft, launched in 1977, have crossed into interstellar space, still transmitting data about conditions beyond the Sun's influence. They carry golden records with sounds and images from Earth, messages for any intelligent beings who might find them millions of years hence, long after the spacecraft have fallen silent. Future missions will probe deeper into the solar system's mysteries. Submarines might explore the oceans of Europa and Enceladus. Balloons could drift through the atmospheres of Venus and Titan. Nuclear-powered spacecraft could reach the Kuiper Belt in years rather than decades. Sample return missions could bring pieces of Mars, asteroids, and comets back to Earth for detailed analysis. The technology developed for solar system exploration drives innovation on Earth. Miniaturized electronics, advanced materials, life support systems, and renewable energy technologies created for space missions find applications in medicine, communications, and environmental protection. The challenge of surviving in space pushes us to develop sustainable technologies essential for Earth's future. Our understanding of the solar system influences philosophy and culture in profound ways. The Copernican revolution, which moved Earth from the center of the universe, fundamentally changed how humanity sees itself. The discovery of deep time through planetary geology gave us perspective on the brevity of human existence. The possibility of life elsewhere challenges anthropocentric worldviews. Children growing up today will likely see humans return to the moon and take first steps on Mars. They might witness the discovery of life beyond Earth or the establishment of permanent space settlements. The solar system that seems so distant and alien to previous generations will become humanity's extended home, with people living and working throughout the inner system and robotic explorers probing ever farther into the outer darkness. The economic development of space could transform human civilization. Asteroid mining could end scarcity of rare elements. Space-based solar power could provide clean energy without Earth's environmental constraints. Manufacturing in zero gravity could produce materials impossible to make on Earth. The wealth generated by space resources could fund solutions to Earth's problems or enable expansion to the stars. Yet space also presents existential risks. An undetected asteroid could devastate civilization. Solar flares could destroy our technology-dependent society. As we spread throughout the solar system, we might fragment into separate species, adapted to different worlds. The technologies that enable space exploration could also be weaponized, extending human conflict beyond Earth. The solar system teaches us patience and humility. Its processes unfold over timescales that dwarf human experience. Mountains on Earth rise and erode away, while Jupiter's great red spot continues spinning. Entire species evolve and go extinct during one orbit of Neptune. This perspective helps us think beyond immediate concerns to consider the long-term survival and prosperity of life. Climate change on Earth gains context from studying other planets. Venus's runaway greenhouse effect shows the danger of too much atmospheric carbon dioxide. Mars's loss of atmosphere demonstrates the importance of a magnetic field and sufficient gravity. These planetary examples inform our understanding of Earth's climate system and the consequences of human activities. The solar system's dynamical stability, maintained for billions of years through subtle gravitational resonances and feedbacks, provides lessons for sustainability. Just as planetary orbits achieve long-term stability through balance and interaction, human civilization must find sustainable balance with Earth's environment. The solar system shows that stability is possible, but not guaranteed, requiring the right conditions and relationships. As our knowledge of exoplanetary systems grows, we appreciate how unusual our solar system might be. The orderly arrangement of small rocky planets inside and gas giants outside, with nearly circular orbits in a flat plane, appears uncommon. Many exoplanetary systems have hot Jupiters orbiting close to their stars or super-Earths in configurations unlike anything in our system. This uniqueness might have been essential for Earth's habitability and life's evolution. The future exploration and settlement of the solar system will require international cooperation unprecedented in human history. No single nation can afford the costs or risks of establishing settlements on Mars or mining asteroids. The Outer Space Treaty and other international agreements provide a framework, but new governance structures will be needed as human activity in space expands. Education about the solar system inspires young people to pursue careers in science, technology, engineering, and mathematics. The wonder of other worlds and the challenge of reaching them motivate students to excel in their studies. The interdisciplinary nature of planetary science, combining physics, chemistry, geology, and biology, demonstrates the interconnectedness of scientific knowledge. Public engagement with solar system exploration builds support for scientific research and space missions. Stunning images from spacecraft like Cassini, Juno, and New Horizons capture imaginations worldwide. Live coverage of Mars rover landings and asteroid sample returns makes everyone part of the adventure. This public interest drives political support for continued exploration. The solar system's story connects us to fundamental questions about existence. How did order emerge from chaos? What makes a world habitable? Are we alone? These questions transcend scientific curiosity, touching on humanity's deepest wonderings about purpose and meaning. The solar system provides a stage where these questions can be explored through both scientific investigation and philosophical contemplation. As we develop the capability to detect and study Earth-like exoplanets, our solar system becomes the template for understanding distant worlds. The processes that shaped our planets operate throughout the universe. The conditions that allowed life on Earth might exist elsewhere. Our solar system, once thought unique and central, becomes one example among billions. yet remains the one we can study in greatest detail. The preservation of solar system heritage sites becomes increasingly important as human activity expands. The Apollo landing sites on the Moon, the Viking landers on Mars, and other locations of historical significance deserve protection. These sites mark humanity's first steps beyond Earth and should be preserved for future generations, like archaeological sites on Earth. Virtual reality and advanced simulation technologies will allow people to explore the solar system without leaving Earth. Students will walk on Mars, fly through Saturn's rings, and dive into Europa's ocean through immersive experiences. These technologies will make solar system exploration accessible to everyone, not just astronauts and wealthy space tourists. The development of closed-loop life support systems for space settlements will revolutionize sustainability on Earth. Technologies for recycling air, water, and waste with near-perfect efficiency, essential for space colonies, could address resource scarcity and environmental challenges on Earth. Space settlements become laboratories for sustainable living that benefit all humanity. The psychological and social challenges of space settlement will teach us about human nature and society. How do small groups maintain cohesion during long space voyages? How do societies develop on worlds with different gravity, day lengths, and environments? These natural experiments in space will provide insights applicable to communities on Earth. The solar system's resources could enable projects of unprecedented scale. Space-based telescopes with mirrors kilometers across could detect signs of life on exoplanets. Particle accelerators circling the Sun could probe the fundamental structure of matter. Vast solar power collectors could provide energy for terraforming Mars or propelling interstellar spacecraft. As artificial intelligence advances, robotic explorers will become increasingly sophisticated. Future probes might make autonomous decisions about what to study, adapt to unexpected discoveries, and even repair or replicate themselves. These intelligent machines could explore environments too dangerous for humans, from Venus's surface to Jupiter's radiation belts. The ethical implications of solar system exploration and exploitation require careful consideration. Do we have the right to terraform Mars if it harbours microbial life? Should we preserve pristine environments or utilise their resources? How do we balance scientific investigation with commercial development? These questions will shape the future of human expansion into space. The solar system provides perspective on environmental changes occurring on Earth. The deep time recorded in planetary surfaces shows that change is normal, but that the rate of current human-caused changes is unprecedented. This geological perspective emphasizes both Earth's resilience over long timescales and its vulnerability to rapid perturbations. Cultural expressions of our relationship with the solar system, through art, literature, music, and film, help process the emotional and spiritual dimensions of space exploration. These creative works inspire wonder, confront fears about cosmic isolation, and imagine possible futures among the planets. They make the solar system part of human culture, not just scientific knowledge. The possibility of planetary defense against asteroid impacts represents the first time life on Earth could prevent its own extinction from cosmic threats. By cataloguing potentially hazardous asteroids and developing deflection technologies, humanity assumes a new role as protector of Earth's biosphere. This capability marks a transition from passive victims of cosmic events to active participants in our own survival. The solar system's example suggests that habitable worlds might be rare and precious in the universe. If Earth is unusual in maintaining stable conditions for billions of years, we bear special responsibility as possibly the only conscious observers in our cosmic neighborhood. This perspective adds moral weight to environmental protection and space exploration. As we conclude this journey through the solar system's past, present, and future, we return to the remarkable fact of our own existence. From cosmic dust to conscious beings capable of understanding our origins, we represent the universe becoming aware of itself. The solar system is not just our home, but the stage where cosmic evolution achieved self-awareness through human consciousness. The story continues with each passing moment. The planets pursue their ancient orbits, while humanity takes its first tentative steps beyond Earth. New discoveries await, from potential life on ocean worlds to exotic physics in extreme environments. The solar system that seemed complete to previous generations reveals new mysteries to each succeeding one. Tonight, as you drift off to sleep, remember that you're riding a planet through space, orbiting a star that orbits a galaxy in an expanding universe. The atoms in your body have travelled through stellar furnaces and interstellar space to arrive at this moment. You are part of the solar system story, a conscious witness to cosmic evolution, briefly awake on a world perfectly positioned to support your existence. The gentle pull of gravity holds you to Earth as it has held the planets in their orbits for billions of years. The same physical laws that govern the grandest structures in the solar system operate within your own body. You are not separate from the cosmos, but woven into its fabric, a temporary arrangement of matter and energy, granted the extraordinary gift of awareness. As sleep approaches, let your mind wander among the worlds we've explored tonight. Picture the rusty dunes of Mars, the swirling clouds of Jupiter, the icy geysers of Enceladus, the methane rain on Titan. These places exist right now, pursuing their own stories whether we observe them or not. They'll continue long after humanity's chapter ends, following the inexorable laws of physics toward their ultimate fates. The solar system cradles us in its gravitational embrace, our extended family of worlds sharing a common origin and destiny. From the searing surface of Mercury to the frozen depths of the Kuiper Belt, from the birth of planets to their eventual destruction, we've traced the arc of cosmic evolution that connects all things. This is our story, written in stone and ice, played out in orbital dances lasting billions of years. Thank you for joining me on this journey through space and time, exploring the magnificent story of our solar system from its humble beginnings in a collapsing cloud of gas and dust to its eventual fade into cosmic darkness. As you drift into sleep, carry with you the wonder of worlds beyond Earth, the vastness of time before and after us, and the precious rarity of this moment when life contemplates its cosmic home. If you enjoyed falling asleep to the entire story of our solar system, from its formation through its incredible diversity of worlds to its ultimate future, please consider subscribing to hear more epic space stories that will carry you gently into peaceful sleep. Like this video if it helped you relax and learn something new about our cosmic neighborhood. Sweet dreams. And remember, you're made of star stuff floating on a rock through space, part of the greatest story ever told.